At the heart of a distant galaxy, something devours matter on a scale that rewrites the rules of physics. The black hole consumes entire stars in moments. It weighs as much as 40 billion suns. The numbers are so extreme that when astronomers first measured them, they assumed their instruments had malfunctioned. They ran the calculations again. The results held. What they had found should not exist according to every model of how black holes form and grow across cosmic time. This is not a typical supermassive black hole sitting at the center of a normal galaxy. This is something else entirely. The object resides more than 10 billion light-years away, which means we observe it as it existed when the universe was barely a quarter of its current age. At that early epoch, there simply had not been enough time for a black hole to accumulate 40 billion solar masses through any known mechanism. The mathematical impossibility sits there in the data, undeniable and troubling. The discovery came through years of painstaking observation. Astronomers studying distant quasars noticed something peculiar about one particular source. The luminosity measurements kept climbing higher. The emission lines in the spectrum suggested velocities of material orbiting at thousands of kilometers per second. When researchers calculated the mass required to generate such extreme motion, the number shocked them. 40 billion times the mass of our Sun compressed into a region smaller than our solar system. The density staggers the imagination. Here is where the problem reveals itself. Black holes grow through two primary pathways. They can merge with other black holes, combining masses in violent collisions that send gravitational waves rippling through space-time. Or they can accrete matter, pulling in gas and dust and stars from their surroundings. Both processes take time. Mergers require black holes to find each other across vast cosmic distances. Accretion faces physical limits on how quickly matter can fall inward. There is a maximum rate called the Eddington limit, determined by the balance between gravitational pull and radiation pressure. Matter falling onto a black hole heats up and emits light. That light pushes outward on additional incoming material. Push too hard and you shut off your own food supply. Calculate the growth trajectory. A black hole that forms from a single massive star might start with 100 solar masses. To reach 40 billion solar masses through accretion alone, it must feed continuously at or near the Eddington limit for the entire history of the universe up to that point. But the universe was only about 3 billion years old when this monster already existed. Run the numbers. The growth rate required exceeds what physics allows by factors of 10 or more. Something does not add up. The alternative pathway faces similar problems. Maybe the black hole grew through mergers rather than accretion. But where did all those smaller black holes come from? Each one would need to form and then somehow migrate to the center of the host galaxy. The galaxy itself must have assembled remarkably early to serve as the gravitational well that collects these black holes. Simulations of structure formation in the early universe struggle to produce such massive systems so quickly. The cosmic web of dark matter grows through hierarchical assembly. Small structures form first, then gradually merge into larger ones. Building a galaxy massive enough to host a 40 billion solar mass black hole in just 3 billion years pushes against the observed pace of cosmic evolution. Think about that for a moment. We observe this black hole as it existed billions of years ago. The light we detect today left that system when the universe was young. Since then, another 7 billion years have passed. The black hole could be even more massive now. We cannot know its current state. We observe only ancient light, frozen photons that traveled across expanding space to reach our telescopes. What we see is already history. Multiple teams verified the measurements independently. The Sloan Digital Sky Survey initially catalogued the quasar. Follow-up observations with larger telescopes confirmed the extreme mass estimate. Radio telescopes measured the extent of jets launched from near the event horizon. Infrared observations probed the surrounding galaxy. Every measurement pointed to the same unsettling conclusion. This object is real. It is not an artifact of faulty data or mistaken analysis. Nature has produced something our theories struggle to explain. The mass estimates rely on analyzing the motion of material around the black hole. Gas clouds and stars orbit the central mass. Their velocities depend on the gravitational pull they experience, which depends directly on how much mass sits at the center. Measure the velocities, measure the distances, and you can calculate the central mass using basic orbital mechanics. The technique is well established. We use the same method to measure the mass of the black hole at the center of our own Milky Way galaxy. That black hole weighs 4 million solar masses. It took decades of tracking individual stars on precise orbits to determine that mass. For distant quasars, we cannot resolve individual orbits. Instead, we measure broader signatures in the light spectrum. The width of emission lines tells us how fast gas is moving. The luminosity tells us how much matter is accreting. The variability timescales tell us how compact the emission region must be. All these measurements converge on the same answer: 40 billion solar masses. This raises uncomfortable questions about the early universe. If such massive black holes existed when the cosmos was young, what does that tell us about the conditions shortly after the Big Bang? Standard models suggest that the first stars formed a few 100 million years after the Big Bang. These first stars were massive and short-lived. When they died, they could leave behind black holes of perhaps 100 to 1,000 solar masses. That provides seed masses for the growth process. But getting from 1,000 to 40 billion requires more than 3 orders of magnitude of growth. That is a factor of 40 million. Even feeding continuously at the theoretical maximum rate, the timescale does not work. Some researchers propose alternative formation pathways. Perhaps the seeds were not stellar black holes at all. Maybe direct collapse created intermediate mass black holes of 10,000 or even 100,000 solar masses very early in cosmic history. Under special conditions, massive clouds of primordial gas could collapse directly into black holes without forming stars first. This skips the stellar evolution stage and provides bigger seeds. Starting from 100,000 solar masses, you need less than 3 orders of magnitude of growth to reach 40 billion. That makes the timeline more feasible, though still challenging. But direct collapse requires very specific conditions. The gas must remain almost perfectly smooth, with no turbulence or magnetic fields to disrupt the collapse. It must cool efficiently without fragmenting into smaller structures. The requirements are stringent. Whether such conditions existed frequently enough to explain all the massive black holes we observe remains debated. The black hole does not sit in isolation. It resides at the center of a massive galaxy, one of the most massive systems known at that cosmic epoch. The galaxy contains hundreds of billions of stars. Its total mass, including dark matter, probably exceeds 1 trillion solar masses. Building such a massive galaxy so early in cosmic history presents its own puzzle. Galaxies grow through mergers, consuming smaller neighbors and gradually increasing in size. But again, the timescale matters. 3 billion years seems insufficient for enough mergers to produce something this massive. Yet there it is. The relationship between black hole mass and host galaxy properties adds another layer. In the local universe, we observe a tight correlation. More massive galaxies host more massive central black holes. The black hole mass typically amounts to about 0.1% of the total stellar mass of the galactic bulge. This correlation holds across 4 orders of magnitude in mass. It suggests that black holes and galaxies grow together through some coupled process. Feedback from the black hole regulates star formation in the galaxy. Mergers that grow the galaxy also feed the black hole. The two components evolve in lockstep. But at early times, this correlation appears different. Some distant quasars show black holes that are overmassive relative to their host galaxies. The black hole grew faster than the galaxy. This suggests that the growth mechanisms operated differently in the early universe. Perhaps black holes grew through super-Eddington accretion, exceeding the theoretical limit through mechanisms we do not fully understand. Perhaps mergers were more frequent in the dense, early universe. Or perhaps the seeds were indeed more massive to begin with, giving black holes a head start. Before you drift off, leave a comment. What time is it where you are right now? And where in the world are you watching from? It helps to know who else is out there contemplating these cosmic mysteries under their own patch of sky. The implications extend beyond this single object. If one black hole can reach 40 billion solar masses so early, others likely exist. Surveys have found multiple ultra-massive black holes in the young universe. Each one presents the same timing problem. Together, they suggest that black hole formation and growth operated more efficiently than our standard models predict. This has consequences for our understanding of structure formation, galaxy evolution, and the history of cosmic reionization. When the first galaxies and black holes turned on, their light and energy output began reionizing the hydrogen gas that filled space. The timing and intensity of this process depend on how quickly black holes and galaxies grew. If massive black holes appeared earlier and in greater numbers than expected, they would have contributed more to reionization than we currently account for. The search continues for even earlier and more massive examples. Next-generation telescopes will probe deeper into cosmic time, examining the first billion years after the Big Bang. If we find 40 billion solar mass black holes at even earlier epochs, the formation problem becomes more acute. At some point, the constraints become so tight that new physics becomes necessary. Perhaps black holes can grow through exotic mechanisms we have not yet identified. Perhaps the seeds formed through processes that only operated in the unique conditions of the very early universe. This particular black hole serves as a laboratory for extreme physics. Near the event horizon, gravity warps space-time so severely that relativistic effects dominate. The rotation of the black hole drags space-time itself into motion. Jets of material launch from the poles at nearly the speed of light, powered by magnetic fields that tap the rotational energy. The accretion disk glows with the light of trillions of suns, visible across billions of light years. In that environment, every prediction of general relativity gets tested to its limits. The black hole also represents an endpoint. Nothing that crosses the event horizon can return. Information falls in, and according to classical general relativity, it is lost forever. This conflicts with quantum mechanics, which insists that information must be preserved. The resulting paradox has troubled physicists for decades. Resolutions typically invoke quantum gravity effects that become important at the horizon, modifying the classical description. But we have no complete theory of quantum gravity. Black holes remain the place where our two fundamental theories, general relativity and quantum mechanics, refuse to reconcile. An object as massive as this one makes the tension more acute. The stakes are higher, the horizon is larger. The quantum effects, if they exist, must operate on scales we can scarcely imagine. Yet here it sits in the data. Real, massive, impossible, waiting for us to understand how it came to be. The discovery represents both a crisis and an opportunity. A crisis because it threatens our models of cosmic evolution. An opportunity because it reveals gaps in our understanding, pointing toward new physics waiting to be discovered. The universe has produced something we did not predict. That is when science advances, when nature surprises us, when the observations refuse to fit the theory. That is when we learn what we had wrong. That is when we discover what we did not know we did not know. The light from this black hole has traveled for 10 billion years to reach us. In that time, the universe has expanded. Galaxies have moved apart. The cosmic microwave background has cooled. New stars have formed and died. Our own solar system came into existence. Life arose on Earth. All while photons from this distant quasar streamed through space, carrying information about an impossible object in a young universe. We are only now learning to read that information. We are only now beginning to understand what it tells us. The information arrives encoded in light. Every photon that reaches us from that distant quasar carries details about the physical conditions near the event horizon, the wavelength event horizon. The wavelengths tell us about temperature. The intensity tells us about luminosity. The spectrum reveals which elements exist in the accretion flow. But extracting meaning from these signals requires understanding the fundamental processes at work. What actually happens when 40 billion solar masses concentrate into a region smaller than our solar system? Gravity dominates everything. At the event horizon, the escape velocity equals the speed of light. This is the defining boundary of a black hole. Inside this radius, nothing escapes. Not matter, not light, not information according to classical physics. For a 40 billion solar mass black hole, the event horizon stretches to about 120 billion kilometers in diameter. That is roughly 800 times the distance from Earth to the Sun. Vast by human standards. Minuscule compared to the galaxy that hosts it. The entire structure that traps light forever occupies less space than the orbit of Pluto if scaled down to solar system dimensions. But the event horizon marks only the point of no return. The gravitational influence extends far beyond. Material can orbit stably at distances many times larger than the horizon itself. The innermost stable circular orbit sits at about 3 times the horizon radius for a non-rotating black hole. For a rotating black hole, it can be even closer. At this innermost orbit, matter whips around at a significant fraction of light speed. The orbital velocity reaches tens of thousands of kilometers per second. Matter moving that fast heats up through friction and compression. It glows. This glowing material forms what astronomers call an accretion disk. Gas and dust spiral inward, gradually losing angular momentum through viscous forces and magnetic interactions. As material moves to smaller radii, it accelerates and heats up. The inner regions of the disk reach temperatures of millions of degrees. At these temperatures, atoms cannot hold together. Electrons strip away from nuclei. The matter exists as plasma, a roiling sea of charged particles. This plasma emits radiation across the electromagnetic spectrum. X-rays from the hottest regions near the black hole. Ultraviolet and optical light from slightly cooler zones farther out. Infrared from the outer disk where temperatures drop below thousands of degrees. The total luminosity can be staggering. When matter accretes onto a black hole, it converts mass into energy with an efficiency that makes nuclear fusion look wasteful. Fusion converts about 1% of mass into energy. Accretion onto a black hole can convert 10% or more. Einstein's equation applies directly. Energy equals mass times the speed of light squared. For a black hole consuming 1 solar mass per year, The energy output exceeds that of an entire galaxy of stars. The quasar associated with this 40 billion solar mass black hole shines with the luminosity of more than 100 trillion suns. That brightness makes it visible across 10 billion light-years of space. Here is where conventional growth mechanisms hit a wall. That incredible luminosity creates pressure. Photons carry momentum. When radiation streams outward from the accretion disk, it pushes on any matter trying to fall in. The outward radiation pressure can become strong enough to balance the inward gravitational pull. This balance defines the Eddington limit. Above this threshold, the radiation pressure exceeds gravity. The black hole effectively shuts off its own food supply by shining too brightly. The Eddington luminosity depends on mass. More massive black holes have higher Eddington limits, but the relationship is linear. Double the mass and you double the maximum luminosity. Calculate what this means for growth. If a black hole accretes exactly at the Eddington limit continuously, its mass increases exponentially with a characteristic timescale of about 40 million years. This is called the salpeter time. Starting from 100 solar masses, you need about 14 salpeter times to reach 40 billion solar masses. 14 times 40 million years equals 560 million years. That seems reasonable. The universe was 3 billion years old when we observed this quasar. 560 million years fits comfortably within that span. But there is a problem. Actually, several problems. First, black holes do not accrete continuously at the Eddington limit. They feed episodically. Sometimes matter flows inward rapidly. Sometimes the supply dwindles. The duty cycle, the fraction of time spent actively accreting, probably averages 50% or less. That doubles the required growth time to over 1 billion years. Second, the seed black holes themselves take time to form. The first stars did not appear until a few 100 million years after the Big Bang. If stellar black holes provide the seeds, that is a few 100 million years lost from the available growth time. Third, and most troubling observations suggest these early black holes grew even faster than the Eddington limit predicts. They somehow exceeded what should be a hard physical boundary. Think of it like trying to fill a bathtub with a faucet that pushes water away as fast as you pour it in. The harder you push water toward the drain, the more forcefully it splashes back out. There exists an equilibrium point where inflow matches outflow. Exceed that point and you cannot add more water no matter how hard you try. Black holes face this exact constraint, yet somehow they bypassed it. The observations demand it. The mass measurements allow no other conclusion. Some researchers propose that black holes might accrete in brief bursts of super-Eddington accretion. Perhaps the geometry of the accretion flow allows matter to fall in from certain directions while radiation escapes in other directions. If the disk becomes thick and puffy rather than thin and flat, photons might get trapped in the flow, reducing the effective radiation pressure. The matter continues falling inward even as the luminosity exceeds the classical Eddington limit. Simulations show that such configurations are possible under specific conditions. The disk must be dense enough and geometrically thick. Magnetic fields must channel the radiation into beams rather than letting it spread in all directions. These requirements are special, but perhaps not impossible. Another possibility involves the seeds themselves. If black holes formed with initial masses of 100,000 solar masses or more through direct collapse, the required growth drops significantly. Starting from 100,000 solar masses, you need only about 9 salpeter times to reach 40 billion. That is about 360 million years of continuous Eddington-limited growth. More plausible, though still requiring nearly perfect conditions. Direct collapse scenarios invoke pristine gas clouds that avoid fragmenting into stars. Such clouds must cool efficiently through molecular hydrogen emission, but not form the heavy elements that would cause the gas to fragment. The conditions existed in the early universe, but whether commonly enough remains uncertain. The environment of the early universe may have facilitated rapid growth in ways that do not operate today. The average density of matter was higher. Galaxies sat closer together. Mergers were more frequent. Each merger dumps fresh gas toward the center where the black hole feeds. The collective feeding history across multiple mergers could accelerate growth beyond what a single steady accretion episode allows. But modeling this process requires simulating entire galaxies evolving over billions of years while simultaneously tracking the black hole growth. The computational challenge is immense. Current simulations provide hints, but not definitive answers. Magnetic fields introduce additional complexity. Observations reveal that quasars launch powerful jets from their poles. These jets contain plasma moving at 99% of light speed or faster. The jets extend for hundreds of thousands of light years, far beyond the host galaxy. Something must accelerate particles to these extreme velocities. The leading theory invokes magnetic fields threading the accretion disk and anchored in the spinning black hole. As the black hole rotates, it drags space-time and the magnetic field with it. This twisting field extracts rotational energy and channels it into the jets. The process is called the Blandford-Znajek mechanism, proposed in 1977 by Roger Blandford and Roman Znajek. For this mechanism to work, the black hole must spin rapidly. A non-rotating black hole cannot launch jets efficiently. The rotation rate determines how much energy can be extracted. A maximally rotating black hole spinning at the theoretical limit can convert up to 42% of its rest mass energy into jet power over its lifetime. That is an astonishing efficiency. It suggests that spinning black holes are not just gravitational sinks, but active engines, converting infalling mass into kinetic energy that shapes their surroundings across cosmic scales. The jets themselves influence black hole growth. They inject energy into the surrounding gas, heating it and sometimes pushing it away from the galaxy entirely. This negative feedback can suppress star formation and slow black hole accretion. Observations show that the most massive galaxies in the local universe have relatively low star formation rates, despite containing enormous reservoirs of gas. The central black holes likely regulate the process. Their jets and winds prevent gas from cooling and collapsing into new stars. Over billions of years, this feedback shapes the relationship between black holes and galaxies, creating the correlation we observe between black hole mass and galactic bulge mass. Yet, in the early universe, this feedback apparently failed to prevent black holes from reaching extreme masses. The 40 billion solar mass example grew, despite whatever feedback operated. Perhaps the supply of gas was so abundant that feedback could not keep up. Perhaps the black hole went through phases of rapid growth separated by quiescent periods, allowing it to exceed its long-term average growth rate during brief episodes. Or perhaps the physics of feedback operates differently at high redshift, in denser environments with different gas compositions. Measuring these black holes from across billions of light years requires sophisticated techniques. Astronomers use what is called reverberation mapping to probe regions close to the event horizon. The central black hole varies in brightness over days to months as the accretion rate fluctuates. This varying light illuminates surrounding clouds of gas, causing them to brighten and dim in response. But the response comes with a time delay. Light from the central source reaches Earth directly. Light that first illuminates the surrounding clouds travels a longer path and arrives later. By measuring this delay, astronomers can determine the physical size of the emission region. Combine that size with the velocity of the gas, measured from spectral line widths, and you calculate the central mass. For extremely distant quasars, reverberation mapping becomes difficult. The time delays stretch to months or years in the observer's frame due to cosmological time dilation. Monitoring campaigns must last years to capture complete variability cycles. Many teams have undertaken such campaigns, building up statistics on black hole masses across cosmic time. The James Webb Space Telescope, launched in 2021, now contributes to these efforts with unprecedented infrared sensitivity. It can detect fainter quasars at higher redshifts, probing even earlier epochs. The discovery of ultra-massive black holes in the young universe has accelerated in recent years. What once seemed like rare anomalies now appear more common. As surveys deepen and telescope capabilities improve, more examples emerge. This shifts the question from whether such objects exist to how frequently they form. The number density of 40 billion solar mass black holes at early times constrains formation models. Too many, and you need extremely efficient growth mechanisms or very massive seeds. Too few, and perhaps they represent the extreme tail of a distribution, statistical outliers that do not require new physics. What happens next depends on observations we have not yet made. Future surveys will map the distribution of black hole masses across all epochs. They will test whether the Eddington limit truly constrains growth or whether nature found workarounds. They will search for the seeds, the first black holes that formed, and determine their masses and formation pathways. Each new measurement refines our understanding or reveals new puzzles. The 40 billion solar mass black hole stands as a signpost, marking territory where our theories venture into uncertainty. The story begins with darkness visible. In 1963, astronomer Martin Schmidt was studying a peculiar radio source catalogued as 3C273. The object looked like a faint star in optical photographs, but its radio emission suggested something far more powerful. Schmidt obtained a spectrum with the 200-inch Hale telescope on Palomar Mountain. What he saw made no sense initially. The emission lines appeared at wavelengths where no known elements produce features. He stared at the pattern for weeks. Then the realization struck him. The lines were not exotic. They were ordinary hydrogen, oxygen, and other common elements. They had just been shifted dramatically toward longer, redder wavelengths by the expansion of the universe. The object was not a nearby star. It sat more than 2 billion light-years away. Calculate the implications. To appear as bright as a faint star, despite being billions of light-years distant, the object must be radiating with the power of trillions of suns. Yet it occupied a tiny region of space. Variability in its brightness over weeks indicated the emission region could be no larger than a few light weeks across. What could generate such immense power from such a compact volume? Schmidt had discovered the first quasar, though the term would not be coined until later. The name comes from quasi-stellar radio source. These objects looked almost like stars, but were clearly something else entirely. The physics community struggled to explain quasars. Some proposed that they were not distant at all. Maybe the redshifts came from some other mechanism, not cosmic expansion. Maybe the objects sat nearby and had been ejected from galaxies at high velocity, producing redshift through the Doppler effect. But this required accelerating enormous masses to relativistic speeds, which seemed even more implausible than accepting the cosmological distances. By the EUE, the consensus settled on the distant interpretation. Quasars were real, they were far away, and they were extraordinarily luminous. The energy source remained mysterious. In 1964, Edwin Salpeter and Yakov Zeldovich independently proposed that massive black holes could power quasars through accretion. Matter falling into a deep gravitational well releases energy. A black hole provides the deepest well possible. Donald Lynden Bell developed the theory further in 1969, calculating the efficiency of energy conversion and the expected spectrum of radiation. His models showed that accretion onto a massive black hole could naturally produce the observed luminosities and spectral properties. The theory gained traction not because anyone had direct evidence for black holes, but because no alternative explanation worked as well. Observations accumulated through the AND. Astronomers catalogued thousands of quasars at various distances. They noticed patterns. Quasars were common at high redshifts, corresponding to the universe when it was a few billion years old. They became rarer at lower redshifts in the more recent universe. This suggested that quasar activity peaked early in cosmic history and declined over time. But why? If supermassive black holes power quasars, what changed? The black holes did not disappear. Perhaps they simply ran out of fuel. As galaxies matured, they consumed their available gas, leaving less material to feed central black holes. The quasars faded not because the black holes vanished, but because the accretion rates dropped. This led to a bold prediction. If every bright quasar in the early universe hosted a supermassive black hole, and if those quasars later faded as fuel supplies dwindled, then massive black holes should exist in the centers of many nearby galaxies today. They would be quiescent, barely accreting, shining faintly, or not at all. But they should still be there. Dormant engines waiting for fresh fuel. The search for these dormant black holes began in earnest in the Dune. The Hubble Space Telescope, launched in 1990 and repaired in 1993, provided the necessary resolution to study the centers of nearby galaxies. Astronomers measured the velocities of stars and gas very close to galactic nuclei. If a massive concentrated object sat at the center, it would influence these velocities in detectable ways. Galaxy after galaxy revealed the same signature. Stars near the center moved faster than could be explained by the visible matter alone. Something massive and dark lurked there. By the late Date, the evidence became overwhelming. Supermassive black holes were common, perhaps universal, in the centers of large galaxies. The Milky Way's own black hole became a target for intensive study. Throughout the ANDT, teams led by Andrea Ghez at UCLA and Reinhard Genzel in Germany tracked individual stars orbiting the galactic center. They measured positions with exquisite precision over decades, mapping out complete orbital trajectories. One star, designated S2, completes an orbit in just 16 years. Its closest approach brings it within 17 light hours of the central mass. At that distance, orbital velocities reach 5,000 kilometers per second. The orbit is highly elliptical. The motion follows Kepler's laws precisely. Only one explanation fits. A single massive object sits at the orbital focus. Its mass amounts to 4 million times the mass of the Sun. Its radius must be smaller than the orbit of Mercury, or else the star would collide with it. A 4 million solar mass object compressed into such a small volume can only be a black hole. Ghez and Genzel shared the 2020 Nobel Prize in Physics for this work, along with Roger Penrose for his theoretical contributions to black hole understanding. But 4 million solar masses seemed small compared to the most luminous quasars. If quasars required billions of solar masses to generate their extreme luminosities, where were those monster black holes today? Surveys began finding them. The galaxy M87, about 54 million light-years away, harbors a central black hole of 6.5 billion solar masses. This mass was first estimated through gas dynamics in the AUS, then refined through stellar dynamics measurements. In 2019, the Event Horizon Telescope collaboration released the first direct image of M87's black hole shadow. 8 radio telescopes spread across the Earth combined their data to achieve resolution equivalent to a telescope the size of the planet. The image showed a dark region surrounded by a bright ring of emission. The dark region marks where light falls into the black hole. The bright ring traces photons that barely escaped, bent into circular trajectories by the immense gravity. The diameter of the shadow matched predictions from general relativity for a 6.5 billion solar mass black hole. Theory and observation aligned. Other ultra-massive examples emerged. The galaxy NGC 4889 may host a black hole of 21 billion solar masses. The galaxy NGC 1600 contains an estimated 17 billion solar mass black hole. These measurements push techniques to their limits. The stars and gas sit far from the black hole even in projection on the sky. Velocities are lower, making the gravitational influence harder to detect. Uncertainties grow, but the trend is clear. The most massive galaxies contain the most massive black holes. The correlation holds across 4 orders of magnitude in mass. Then came discoveries pushing further back in time. In 2001, the Sloan Digital Sky Survey began operations. This ambitious project mapped large fractions of the sky, cataloging millions of galaxies and quasars. Automated spectroscopy allowed rapid classification of objects. Within a few years, SDSS had discovered numerous high redshift quasars. Some dated from when the universe was less than 1 billion years old. Their central black holes weighed billions of solar masses despite the young age. The timing problem became acute. The quasar ULAS J1120-120641, discovered in 2011, sits at a redshift of 7.1. Its light was emitted just 770 million years after the Big Bang. Its black hole weighs 2 billion solar masses. How did it grow so massive so quickly? The discoverers calculated that even starting from a 1,000 solar mass seed and accreting continuously at the Eddington limit, the growth time would be about 700 million years. That left only 70 million years for the seed to form and begin growing. The margins were razor thin. Subsequent discoveries found even earlier examples. The quasar ULAS J1312-120928, announced in 2017, has a redshift of 7.5. The universe was only 690 million years old. Its black hole weighs 800 million solar masses. The quasar J0313-1806, discovered in 2021, exists at redshift 7.6, corresponding to 670 million years after the Big Bang. Its black hole exceeds 1.5 billion solar masses. Each new record pushed the formation epoch earlier and made the growth requirements more severe. These discoveries did more than challenge models. They opened windows into the epoch of reionization. Between about 400 million and 1 billion years after the Big Bang, the universe underwent a fundamental transition. Initially, space was filled with neutral hydrogen atoms. The first stars and galaxies began ionizing this hydrogen, splitting atoms into protons and electrons. Eventually, essentially all the hydrogen in intergalactic space became ionized. This process was patchy. Ionized bubbles formed around the first galaxies and gradually merged. Quasars contributed to this reionization through their intense ultraviolet radiation. By studying the spectra of high redshift quasars, astronomers can probe the ionization state of the intervening hydrogen. Specific absorption features called Gunn-Peterson troughs reveal neutral hydrogen along the line of sight. The strength and distribution of these troughs constrain when reionization occurred. The quasars themselves served as backlights, illuminating the universe at crucial moments in its history. Without them, we would know far less about the evolution of the intergalactic medium. Their extreme luminosities make them visible across vast distances and timescales. They are cosmic lighthouses, marking the growth of structure in the early universe. Each one represents not just a massive black hole, but an entire galaxy forming and evolving rapidly. The James Webb Space Telescope, which began science operations in 2022, is now finding even more examples. Its infrared sensitivity allows it to detect heavily obscured quasars, missed by optical surveys. Some of these newly discovered black holes are growing while shrouded in thick clouds of dust. The dust absorbs ultraviolet and optical light, reprocessing it into infrared. This changes how we estimate black hole masses and accretion rates. The population of growing black holes in the early universe may be larger than previously recognized. Technology drove each breakthrough. Schmidt's 1963 discovery relied on the largest optical telescope available. The Sloan Digital Sky Survey required digital cameras capable of imaging large sections of sky simultaneously. The Event Horizon Telescope needed atomic clocks, precise time stamping, and petabytes of data storage. The James Webb Space Telescope demanded innovations in infrared detector technology, mirror fabrication, and passive cooling systems. Each advance revealed phenomena invisible to previous instruments. Each generation of astronomers looked deeper, saw further, and found the unexpected. What ties these discoveries together is a progressive realization that black holes are not rare cosmic curiosities, but fundamental components of galaxy evolution. They influence star formation. They regulate gas cooling. They launch jets that reshape the intergalactic medium. Their growth parallels the growth of galaxies. Understanding one requires understanding the other. The 40 billion solar mass black hole represents an extreme in this population. But it is part of a continuum. It illuminates the high mass end of the distribution. It tests whether the same physical processes that operate at lower masses scale up to these extremes, or whether new phenomena emerge. The historical arc bends toward increasing strangeness. Each decade brought surprises. Quasars existed. They were powered by black holes. Those black holes were massive. They formed early. They grew impossibly fast. They influenced cosmic reionization. They correlated with galaxy properties. They merged and released gravitational waves. They approached masses that seemed theoretically forbidden. The pattern is not one of steady refinement, but repeated upheaval. Nature kept producing objects that stretched or broke theoretical expectations. Astronomers responded by expanding their models, invoking new processes, and designing new observations. The conversation between theory and observation continues. The 40 billion solar mass black hole is the latest word, not the last. The 40 billion solar mass black hole does not exist in isolation. It sits embedded in a vast cosdid in a vast cosmic web, a network of matter that stretches across the observable universe. Understanding this context reveals why the black hole's mass is not just large, but impossibly large. The web determines where matter concentrates. It channels gas toward galaxies. It sets the pace of structure formation. And by every measure we have, the web should not have been able to feed a black hole to 40 billion solar masses in the time available. Picture the universe on the largest scales. Galaxies are not randomly scattered. They cluster along filaments, cosmic highways of dark matter, and gas that connect dense nodes. Between these filaments stretch vast voids, regions of space with few galaxies. The web forms through gravitational instability. Tiny density fluctuations in the early universe, quantum fluctuations stretched to cosmic size by inflation, grew over time. Denser regions attracted more matter. Underdense regions lost matter to their neighbors. Over billions of years, this process carved out the cosmic web we observe today. The densest nodes in this web, where multiple filaments intersect, become the sites of galaxy clusters. These clusters contain hundreds or thousands of galaxies bound together by gravity. Their total masses reach quadrillions of times the mass of the Sun. At the centers of these clusters sit the most massive galaxies, giant ellipticals that formed through countless mergers. These central galaxies host the most massive black holes. The 40 billion solar mass example resides in just such a location, at the gravitational center of an emerging massive structure. But here is the problem. At the epoch when we observe this black hole, 3 billion years after the Big Bang, the cosmic web was still forming. Clusters had not yet fully assembled. The universe was denser on average than today, which should help structure formation, but specific high-density peaks took time to develop. Simulations of cosmic structure formation start with the initial density field measured from the cosmic microwave background and evolve it forward using gravity. These simulations rarely produce structures massive enough to host 40 billion solar mass black holes at such early times. The tail of the distribution extends to billions of solar masses. Yes, but 40 billion pushes into territory occupied by perhaps one system in the entire observable volume at that epoch. This rarity matters. If the black hole is a 1 in a billion occurrence, its existence might not require new physics. Statistical outliers happen. Measure enough systems and you will find extremes that defy typical behavior. But if multiple such objects exist, and surveys are beginning to find them, the explanation shifts. Outliers become a population. New mechanisms become necessary. The question transforms from whether this black hole can exist to how many similar systems lurk in the cosmos awaiting discovery. The environment around the black hole shaped its growth. Gas must flow inward from large scales to feed the central engine. This flow depends on the gravitational potential well, which depends on the total mass distribution, including dark matter. Dark matter provides most of the gravity that binds galaxies and clusters. It outweighs ordinary matter by a factor of 5 or 6. The dark matter halo surrounding the host galaxy acts like a funnel, directing gas toward the center where the black hole feeds. The deeper the potential well, the more efficiently gas falls inward. The most massive halos channel the most gas. Simulations show that mergers play a crucial role. When two galaxies collide, their gas clouds crash together, lose angular momentum, and sink toward the merged system's center. Both galaxies bring their own central black holes. These black holes orbit each other, gradually spiraling inward through dynamical friction and gravitational wave emission. Eventually they merge, combining their masses in a single event that radiates more power in gravitational waves than all the stars in the observable universe shine in light. The merger also triggers bursts of star formation and black hole accretion. Fresh gas floods the center. The black hole feeds rapidly. Growth accelerates. For the 40 billion solar mass black hole to form, its host galaxy likely underwent numerous major mergers. Each merger added mass and triggered accretion. The cumulative effect, summed over many events, could exceed what steady feeding alone achieves. But this scenario requires a formation history that is both fortuitous and finely timed. The mergers must happen early enough to contribute to growth before the epoch we observe. They must deliver enough gas to enable super-Eddington accretion rates. They must not disrupt the central black hole through gravitational slingshots, which can sometimes eject black holes from their host galaxies. Every step must proceed efficiently. Nature must cooperate at every stage. Measuring the mass of such a distant black hole introduces layers of uncertainty. The techniques rely on indirect signatures. The width of emission lines indicates velocity dispersion. The luminosity indicates accretion rate. The variability timescale indicates compactness. Each observable connects to the central mass through theoretical models. Those models involve assumptions. Gas orbits the black hole in a thin disk. Radiation pressure does not significantly alter the dynamics. The emission region is photoionized by the central continuum source. Magnetic fields do not dominate the dynamics. Violations of any assumption introduce systematic errors. Different methods sometimes produce conflicting results. Reverberation mapping measures the time delay between continuum and emission line variability. This gives a dynamical mass based on the light travel time and velocity. Single epoch spectroscopy uses emission line widths and luminosity combined with empirical scaling relations calibrated on local galaxies. The two methods do not always agree. Discrepancies of factors of 2 or 3 are not uncommon. For a 40 billion solar mass estimate, this means the true mass might be anywhere from 20 billion to 80 billion solar masses. The uncertainty is large in absolute terms, even if relatively small in percentage. Cosmological effects complicate the analysis. Light from the quasar has traveled through expanding space. Wavelengths stretch, timescales dilate. The redshift transforms the observed frame to something different from the emission frame. A fluctuation that takes days in the quasar's frame appears to take weeks in our frame. The factor is 1 plus the redshift. For a quasar at redshift 2, observed timescales are 3 times longer than emitted timescales. This must be corrected when inferring physical sizes from variability. Get the correction wrong, and your mass estimate shifts. Gravitational lensing adds another layer. Sometimes a massive galaxy or cluster sits between us and a distant quasar. The intervening mass bends light, magnifying the quasar's brightness and sometimes producing multiple images. Lensing changes the apparent luminosity. It can make a quasar seem brighter than it actually is. If you estimate the black hole mass using luminosity-based methods without accounting for lensing, you overestimate. Identifying lensed quasars requires careful imaging to detect the multiple images or the lensing galaxy. Not all cases are obvious. Some fraction of high luminosity quasars may be magnified by weak lensing from large-scale structure. This introduces a statistical bias toward overestimating the most extreme masses. Our location in space and time affects what we see. We observe the universe from a particular position in the Milky Way, looking outward through our galaxy's disk and halo. Dust in our galaxy absorbs and scatters light, especially at optical and ultraviolet wavelengths. This obscures objects behind dense regions of our galaxy. Large areas of the sky, particularly toward the galactic plane, remain difficult to survey for distant quasars. We miss objects in those directions. Our census is incomplete. We also observe from a particular moment in cosmic history, 13.8 billion years after the Big Bang. Looking outward means looking backward in time. Light from distant objects left them long ago. We see the 40 billion solar mass black hole as it existed 10 billion years ago. Its current state is unknown and fundamentally unknowable given the speed of light. The black hole has continued evolving. It may have merged with others. It may have consumed additional gas. It may have become more massive. Or its accretion may have shut off, leaving it dormant. We cannot know without waiting billions of years for light from later epochs to arrive. And even then, we only see later snapshots, never the object as it exists simultaneously with us. This temporal offset creates peculiar consequences. We can see objects that no longer exist in any meaningful sense. A galaxy 10 billion light-years away might have merged with a neighbor 5 billion years ago. That merger happened 5 billion years in our past relative to the galaxy's timeline, but is still 5 billion years in our future relative to the light we receive. The galaxy as we observe it is real, in the sense that the light is real and carries accurate information about conditions at emission. But that galaxy no longer exists in its observed form. It has evolved, perhaps transformed beyond recognition. The cosmological horizon adds a fundamental limit. Light travels at finite speed. The universe has finite age. There exists a maximum distance from which light could have reached us since the Big Bang. Beyond this horizon, objects are causally disconnected. We cannot see them. They cannot influence us. The observable universe has a radius of about 46 billion light-years in co-moving coordinates, accounting for expansion during the light travel time. This is not the entire universe. It is just the portion accessible to observation. The full universe may be far larger, perhaps infinite. We cannot know. Regions beyond our horizon are, for all practical purposes, separate universes. We can speculate about conditions there based on our understanding of physics, but we have no direct evidence. The 40 billion solar mass black hole sits well within our observable volume. But how typical is it? If we could observe the entire universe, would we find trillions of similar objects? Or is it genuinely rare, a statistical fluke that required very specific conditions? The question bears on whether our observable patch of the universe is representative. Cosmological principles suggest it should be. The universe appears homogeneous and isotropic on large scales. No direction seems special, no location seems central. This is called the cosmological principle. It guides our understanding of the universe's large-scale structure and evolution. But the principle is statistical. It holds on average across vast volumes. Local fluctuations exist. Our galaxy sits in a somewhat underdense region of the cosmic web, not in a rich cluster. The nearest major cluster, the Virgo cluster, sits about 54 million light-years away. We are on the outskirts of a large structure called the Laniakea supercluster, which spans 500 million light-years. Within this supercluster, matter streams toward a concentration called the Great Attractor. Our local environment is not average. It is below average in density. This affects what we see when we look outward. Our view is colored by our position in the cosmic web. This matters for understanding black hole formation. If black holes grow faster in denser environments, as seems likely, then our local neighborhood might not host the most massive examples. The real monsters form in overdense regions where galaxy mergers are frequent and gas supplies abundant. We observe those regions as they existed in the past, when density contrasts were less extreme than today. Still, the principle suggests that massive black holes should form anywhere given enough time and matter. The fact that we find them at high redshift, when the universe was young, indicates that formation does not require the full age of the cosmos. It can happen quickly under the right conditions. Secondary effects ripple outward from the black hole. The jets launched from near the event horizon propagate through the surrounding medium. They shock the gas, heating it to tens of millions of degrees. This hot gas emits X-rays detectable with space-based telescopes. The jets carve cavities in the ambient medium, pushing material aside and sometimes triggering star formation at the shock fronts. Over millions of years, the jets inject enormous energy into the host galaxy and beyond. This energy changes the thermodynamic state of gas over scales far larger than the galaxy itself. It prevents gas from cooling and falling into new generations of stars. It shapes the evolution of the entire system. Some of this energy escapes the galaxy entirely, depositing into the intergalactic medium. The space between galaxies is not empty. It contains diffuse gas, enriched with elements forged in stars and expelled by supernovae and stellar winds. Quasar outflows and jets contribute additional enrichment. They also heat the gas, affecting its pressure and density. These effects propagate outward at the speed of sound, which in ionized plasma is a few hundred kilometers per second. Over cosmic time, the influence of a quasar can extend tens of millions of light-years from its host galaxy. The black hole does not just affect its immediate surroundings, it reshapes the cosmic web itself on local scales. Why does location in space and time matter? Because context determines possibility. A black hole forming in a low-density region faces different conditions than one forming at the intersection of major filaments. The available gas supply differs. The merger rate differs. The tidal forces differ. Not all locations in the universe are equally favorable for rapid black hole growth. The 40 billion solar mass black hole occupies a special location, one where conditions allowed exceptional growth. Understanding where such locations exist and how common they are constrains how many similar black holes we expect to find. Location in time matters equally. The early universe was denser and hotter. The gas was mostly primordial hydrogen and helium, lacking heavy elements. The cosmic microwave background was brighter, bathing the universe in radiation. Cooling mechanisms differed. Star formation proceeded differently. Black hole seeds formed under conditions unlike anything in the present universe. Those early conditions cannot be recreated or revisited. We study them through observation and simulation, piecing together what must have happened based on what we see today. The 40 billion solar mass black hole is a messenger from that era. It formed under conditions we can only infer. Its existence constrains what those conditions allowed. The measurements do not agree. Two independent methods for determining black hole masses, both well-established and thoroughly tested on nearby objects, produce results that diverge by factors of 2 or more when applied to the most distant quasars. This is not a minor discrepancy that falls within error bars. This is a fundamental disagreement that suggests something is wrong with our assumptions, our techniques, or our understanding of what happens near these extreme objects. The first method relies on reverberation mapping. Observe a quasar continuously over months or years. Measure how its central continuum emission varies in brightness. Watch as broad emission lines from surrounding gas clouds respond to these variations. The lines do not vary instantly. There is a delay. Light from the continuum source must travel outward to illuminate the gas clouds. Only then do the clouds brighten and produce stronger emission lines. Measure this time delay precisely. It tells you the light travel distance to the emission region. Measure the velocity of the gas from the width of the emission lines. Velocity and distance together give you mass through Kepler's laws. The technique is elegant and direct. For nearby active galaxies, reverberation campaigns have measured dozens of black hole masses. The results agree well with independent methods based on stellar dynamics. The technique works. It produces reliable answers. But applying it to distant quasars introduces complications. The time delays stretch to months in the observer's frame due to cosmological time dilation. Monitoring campaigns must run for years to capture complete variability cycles. Weather interrupts observations. Telescope schedules conflict. Funding runs out. Few campaigns achieve the cadence and duration necessary for reliable measurements. The handful that succeed find black hole masses in the billions of solar masses at high redshift. These measurements push the boundaries of what theory predicted. The second method uses single epoch spectroscopy combined with empirical scaling relations. Obtain a single spectrum of a quasar. Measure the width of the broad emission lines. particularly hydrogen sulfur or magnesium. Measure the continuum luminosity at specific rest frame wavelengths. Plug these values into an equation calibrated on local reverberation mapped objects. The equation estimates the time delay based on luminosity. Combined with the velocity, it yields mass. This method is fast. It requires only one observation per object. It scales to large surveys covering thousands of quasars, but it rests on the assumption that high redshift quasars follow the same scaling relations as local objects. Here is where the trouble begins. When both methods are applied to the same high redshift quasars, they sometimes give different answers. Reverberation mapping tends to produce higher masses. Single epoch spectroscopy gives lower masses for the same object. The discrepancy averages about a factor of 2, but reaches factors of 3 or 4 in extreme cases. For a 40 billion solar mass estimate from single epoch spectroscopy, reverberation mapping might yield 80 billion or even 100 billion solar masses. Which number is correct? Several explanations have been proposed. Perhaps the scaling relations evolved over cosmic time. Local quasars, observed in the present-day universe, might have different physical conditions than ancient quasars in the young universe. Gas densities could differ. Ionization states could differ. The geometry of the emission region could differ. If high redshift quasars deviate systematically from the local relations, applying those relations produces biased results. The bias could go either direction depending on which physical property changed and how. Another possibility involves selection effects. The quasars bright enough to detect at high redshift might not be typical. They might represent a specific mode of black hole growth characterized by higher than average accretion rates or unusual emission line properties. If we calibrate scaling relations on local objects that span a range of properties, but then apply them to high redshift objects that occupy only one corner of that range, we extrapolate incorrectly. The bias enters through which objects we can observe, not through changes in physics. Gravitational lensing contaminates some measurements. If a foreground mass magnifies a quasar's brightness, luminosity-based methods overestimate the intrinsic luminosity. This leads to overestimating the black hole mass. But lensing should not affect reverberation mapping, which depends on time delays and velocities rather than absolute luminosities. If single epoch masses are inflated by unrecognized lensing while reverberation masses are not, we would see single epoch masses exceed reverberation masses. The pattern goes the opposite direction. Reverberation produces higher estimates. Lensing cannot explain the discrepancy. Orientation effects introduce another complication. We view quasars from random angles. Some we see face-on, looking down the axis of the accretion disk. Others we see edge-on, looking through the disk plane. The viewing angle affects both the observed luminosity and the emission line widths. Face-on systems show narrower lines because we are not viewing velocities along our line of sight. Edge-on systems show broader lines from Doppler shifts of material moving toward and away from us. If high redshift quasars preferentially have certain orientations, either due to selection effects or alignment with cosmic structure, the scaling relations fail. Dark matter in the emission region has been invoked. If dense concentrations of dark matter orbit close to the black hole, they contribute additional mass without producing light. Techniques that measure mass from the velocities of luminous gas would overestimate the black hole mass, attributing dark matter to the black hole itself. But dark matter concentrations near black holes should be disrupted by tidal forces. Material that close to the event horizon experiences enormous gravitational gradients. Dark matter particles feel those gradients just as gas does. They should spread out or fall in. Maintaining a stable dark matter population close enough to matter requires special conditions. Most researchers consider this scenario unlikely. super-Eddington accretion may alter the emission line regions. When accretion rates exceed the Eddington limit, radiation pressure becomes extreme. The disk puffs up, becoming thick and geometrically inflated. Powerful winds launch from the disk's surface. These winds can reach velocities of thousands of kilometers per second. If some of the broad line emission comes from wind material, rather than orbiting gas, the line widths no longer trace the gravitational potential accurately. They include a wind velocity component that has nothing to do with Keplerian orbits. Mass estimates based on line widths become systematically too high. They mistake wind velocities for orbital velocities. Testing these explanations requires detailed observations. High-resolution spectroscopy can potentially distinguish orbital motion from outflow motion. Orbits produce symmetric line profiles, blue-shifted and red-shifted components that mirror each other. Outflows produce asymmetric profiles, with blue-shifted components enhanced if we view the wind approaching. Multi-wavelength observations reveal different aspects of the system. X-ray observations probe the innermost accretion flow. Infrared observations penetrate dust that might obscure optical emission. Radio observations trace jets and large-scale structure. Combining all these data constrains the geometry and kinematics. The stakes extend beyond individual objects. The mass function of black holes across cosmic time informs models of galaxy evolution, cosmological structure formation, and gravitational wave backgrounds. If we systematically overestimate or underestimate masses at high redshift, we misunderstand how quickly black holes grew and how common different masses were at different epochs. This propagates into models of quasar feedback, cosmic rionization, and the merger history of black holes. Get the masses wrong, and you get the entire growth history wrong. Recent work with the James Webb Space Telescope is helping to resolve some uncertainties. Its infrared spectroscopy cuts through dust that obscures optical observations. It detects emission lines redshifted into the infrared from high redshift quasars. The superior sensitivity allows measurement of fainter lines that provide independent mass traces. For instance, forbidden emission lines come from gas farther from the black hole, in regions where radiation pressure is lower and motion more accurately traces gravity. These lines should give more reliable mass estimates than broad lines from the inner regions. Initial results suggest that some previous mass estimates were indeed too high by factors of 2 or 3. But even with improved measurements, the fundamental question persists. How did black holes reach tens of billions of solar masses so early? Even if the 40 billion solar mass estimate drops to 20 billion after revised analysis, the problem remains. 20 billion solar masses in 3 billion years still requires near-continuous Eddington-limited accretion starting from large seeds. The timing margins are tight regardless of the exact number. This tension reveals a gap in understanding. Either black holes grew faster than the Eddington limit allows, or they started from more massive seeds than stellar evolution produces, or some combination of both. Super-Eddington growth requires special geometries that trap radiation and reduce effective pressure. Direct collapse seeds require pristine gas clouds that avoid fragmentation. Both scenarios involve conditions that may have been more common in the early universe, but are not well constrained observationally. Competing models make different predictions. Models invoking direct collapse seeds predict that the first black holes should have masses of 100,000 solar masses or more. Models based on stellar remnant seeds predict initial masses of 100 to 1,000 solar masses. The difference is 2 orders of magnitude. Starting from 100,000 solar masses, a black hole needs to grow by a factor of only 400 to reach 40 billion. Starting from 1,000 solar masses, it needs to grow by a factor of 40 million. The required growth time scales proportionally. One scenario needs millions of years of efficient accretion. The other needs hundreds of millions of years. Distinguishing these scenarios observationally proves challenging. The seed phase is brief and faint. Seeds form in the first few 100 million years after the Big Bang, at redshifts beyond even what JWST can easily reach. They accrete and brighten quickly, becoming small quasars that outshine their surroundings. By the time we detect them, they have already grown by factors of 10 or more. We miss the initial state. We see them only after growth is underway. Inferring the seed mass requires extrapolating backward in time using growth models, which introduces circularity. We use models to infer seeds, then use inferred seeds to test models. Gravitational waves from black hole mergers offer an independent constraint. When two massive black holes merge, they emit gravitational waves with frequencies and amplitudes that depend on the component masses. The LIGO and Virgo detectors have observed dozens of mergers involving stellar mass black holes, objects with masses of tens to hundreds of solar masses. Future detectors like LISA, the Laser Interferometer Space Antenna planned for launch in the D2s, will detect mergers of massive black holes weighing thousands to millions of solar masses. These observations will reveal the merger rate across cosmic time and the mass distribution of merging systems. If intermediate mass black holes merge frequently in the early universe, LISA will see their signals. The gravitational wave data will constrain formation pathways independently of electromagnetic observations. Population statistics provide another angle. Count how many black holes exist at different masses and redshifts. The number density evolution constrains growth rates and seed properties. If seeds were massive, we expect fewer objects at intermediate masses because systems grow quickly through that range. If seeds were small, more objects should linger at intermediate masses. Current surveys find roughly equal numbers of quasars at redshifts 2, 3, and 4, but sharply declining numbers at redshift 6 and above. This suggests a transition epoch around redshift 5 or 6, corresponding to about 1 billion years after the Big Bang, when black hole growth accelerated, or when detection becomes difficult due to dust obscuration. Resolving the discrepancy between measurement methods matters profoundly. It determines whether the most extreme objects are real or artifacts. It affects our confidence in the entire high redshift black hole population. It influences how we design future observations and which questions we prioritize. If reverberation masses are correct, black holes are even more massive than single epoch spectroscopy suggests, and the formation problem becomes more severe. If single epoch masses are correct, reverberation mapping has systematic biases at high redshift that we must understand and correct. The community has not reached consensus. Papers present arguments on both sides. Some researchers favor reverberation results, citing direct time delay measurements as more robust than empirical calibrations. Others trust single epoch methods, arguing that they include larger samples and average over stochastic variability that might bias individual reverberation campaigns. The debate continues at conferences and in journal pages. Each new measurement refines the picture or adds new complexity. What happens next depends on observations planned and underway. Multi-epoch spectroscopy campaigns target the brightest high redshift quasars, attempting reverberation mapping at cosmic distances. These campaigns require years of dedicated telescope time and often involve coordination across multiple observatories. The extremely large telescope, under construction in Chile with a planned completion in the late Thewend, will provide the light-gathering power necessary to measure fainter variability signatures. Its 39-meter mirror will collect 15 times more light than the current largest optical telescopes. That sensitivity opens new parameter space for reverberation studies. Meanwhile, theoretical work explores alternative interpretations. Simulations track black hole growth in cosmological contexts, following gas flows from large scales down to accretion disk scales. These simulations test whether standard assumptions hold under early universe conditions. They probe whether super-Eddington accretion occurs naturally or requires fine-tuning. They investigate whether magnetic fields alter accretion efficiency. Each simulation provides predictions that observations can test. Each observation constrains what simulations must explain. The iterative process advances understanding incrementally. Slowly, the contradictions resolve or transform into new questions. The 40 billion solar mass black hole sits at the center of this debate. Its mass depends on which measurement method you trust. Its formation history depends on which growth model you adopt. Its implications for cosmology depend on how common such objects are. Every aspect connects to fundamental uncertainties in our understanding of how structure forms in the universe. The object is simultaneously a discovery and a mystery. We know it exists, we do not fully understand how. The universe appears to operate backwards. In every framework of structure formation, large objects should be rare and late. Small things form first. They merge and grow. Over billions of years, through countless collisions, they build up to larger and larger masses. The biggest structures should emerge last. That is how hierarchical assembly works. That is what the mathematics predicts. That is what simulations show. The 40 billion solar mass black hole violates this principle by existing when the universe was young. It is not just early, it is impossibly early. The expected timeline does not accommodate it. Think of building a mountain. You start with pebbles. Rain and erosion accumulate sediment. Layers compress. Tectonic forces push upward. Millions of years pass. The mountain rises slowly. You cannot jump straight to Everest without the incremental steps. Structure formation in the universe follows similar logic. Dark matter clumps first on small scales. These clumps attract gas. Stars form. Small galaxies appear. They collide and merge. Larger galaxies result. Central black holes combine. The process takes time at every stage. Skipping steps requires mechanisms we have not identified. Yet observations consistently find massive black holes at early times. They emerge in an era when small should dominate. The statistics defy expectations. The more sensitive our telescopes become, the more high redshift quasars we discover. The population does not thin out as rapidly as models predict. Instead of finding rare extremes, we find what looks like a common phenomenon. Something about the early universe facilitated rapid black hole growth more effectively than the present epoch allows. The conditions differed in ways that matter. Simulations struggle to reproduce the observations. Cosmological simulations start from initial conditions set by the cosmic microwave background. They evolve the dark matter distribution forward using gravity. They include gas physics, star formation, supernova feedback, black hole accretion, and quasar winds. Modern simulations track billions of particles across cosmic volumes. They resolve individual galaxies. They follow black hole growth over time. The computational resources involved are staggering. Some simulations require months of runtime on thousands of processors. The results offer detailed predictions for the mass function of black holes at different redshifts. Run these simulations forward to redshift 2 or 3, corresponding to the universe at 3 or 4 billion years old. The simulations produce black holes of a few billion solar masses. This matches observations reasonably well. Push earlier to redshift 6 or 7, the first billion years. The simulations produce smaller black holes, mostly below 1 billion solar masses. Observations find larger ones. The discrepancy grows at earlier times. By redshift 7, simulations underpredict black hole masses by factors of 3 to 10. Something is missing from the models. Several culprits have been identified. Perhaps the simulations underestimate the efficiency of gas accretion in the early universe. The standard prescriptions for how gas cools and falls onto black holes derive from local observations and theory. They might not apply when the universe was denser and hotter. Gas densities were higher. Cooling rates were faster. Fragmentation thresholds might have been different. All these factors influence how rapidly black holes grow. Simulations use simplified models for processes that occur on scales too small to resolve directly. If those models systematically underestimate accretion rates, the resulting black hole masses will be too low. Alternatively, perhaps the seeds were more massive than simulations assume. Most simulations seed black holes from stellar remnants with initial masses around 100 solar masses. This represents the standard expectation from population 3, star evolution. But if direct collapse produced seeds of 100,000 solar masses or more, the entire growth trajectory shifts upward. Feed such a seed at the Eddington limit for a few 100 million years, and you easily reach billions of solar masses. The question becomes how often direct collapse occurred. Simulations that attempt to model direct collapse find that it requires very specific conditions. The gas must be metal-free. It must be irradiated by ultraviolet radiation from nearby sources. The radiation dissociates molecular hydrogen, removing the main coolant, allowing the gas to remain hot and collapse directly. These conditions existed somewhere in the early universe. Whether they existed commonly enough to explain the observed population remains uncertain. Here is where it gets strange. The larger the black hole, the easier it should be to detect. Massive black holes shine more brightly when they accrete. They should stand out in surveys. We should find them preferentially. This introduces selection bias. The detected population represents the brightest tip of the iceberg. For every quasar we observe, many fainter ones escape detection. This means the true population includes more lower mass black holes than we see. Correcting for this bias should make the massive objects seem rarer, not more common. Yet after corrections, the number density of massive black holes at high redshift still exceeds predictions. The tail of the distribution extends too far. Statistical arguments suggest that extreme outliers should be vanishingly rare. If black hole masses follow a log normal distribution, as many properties in nature do, then objects several standard deviations above the mean become exponentially unlikely. A 40 billion solar mass black hole at redshift 2 might represent a 5 or 6 sigma outlier. The probability of finding even one such object in the observable volume becomes less than a few percent. But we appear to have found several. Either the distribution has non-Gaussian tails that extend further than simple models predict, or the objects are not as rare as statistics suggest, or we are seeing the universe during a special phase when extreme objects were more common than at other epochs. An analogy helps illustrate the problem. Imagine observing a forest that is only 10 years old. You expect to find saplings and young trees, perhaps a few that have grown faster than average. You would not expect to find trees 40 meters tall with trunks 2 meters in diameter. Such trees typically take centuries to grow. Finding one in a 10-year-old forest raises questions. Did it grow impossibly fast? Did it have a head start, perhaps sprouting from a large seed or a root system that survived from before? Is the forest actually older than you thought? Or is your model of tree growth wrong? The 40 billion solar mass black hole presents an analogous puzzle. The cosmic forest is young. The tree is impossibly large. Observations confirm that these black holes are real, not artifacts of measurement errors. Multiple independent techniques converge on similar masses. Different telescopes observe the same objects and obtain consistent results. The variability timescales are short, indicating compact emission regions. The luminosities are extreme, requiring massive power sources. The host galaxies are among the most massive known at their respective redshifts. Every piece of evidence supports the existence of ultra-massive black holes in the young universe. The observations are robust. The interpretation remains debated, but the basic phenomena are not in question. Some researchers have proposed alternative frameworks. Perhaps general relativity requires modification at very high densities or in the early universe. Modified gravity theories like MOND, modified Newtonian dynamics, change how gravity operates on certain scales. These theories were originally designed to explain galaxy rotation curves without invoking dark matter. But if gravity behaves differently than Einstein's equations predict, black hole formation and growth might also differ. Stronger gravity at early times could accelerate structure formation. Black holes could accumulate mass faster. The Eddington limit, derived from balancing gravitational and radiation forces, might not apply if the force law changes. Most physicists consider such modifications unlikely. General relativity has passed every test to which it has been subjected. Gravitational wave observations from merging black holes match predictions to exquisite precision. The theory works at scales from solar system dynamics to cosmological distances. Altering it to explain one set of observations risks breaking consistency with many others. Modified gravity remains a fringe idea, pursued by a minority but not widely accepted. Extraordinary claims require extraordinary evidence. Black hole masses, while puzzling, do not yet meet that threshold. Another alternative invokes primordial black holes. These hypothetical objects would have formed directly from density fluctuations in the first fraction of a second after the Big Bang, long before stars existed. If the early universe contained regions where density fluctuations exceeded critical thresholds, those regions could collapse into black holes almost immediately. Such primordial black holes could have any mass depending on the size of the fluctuation. They might range from tiny, less than a gram, to millions or billions of solar masses. If abundant, they could serve as seeds for later growth, or even account for some fraction of dark matter. The problem with primordial black holes is that we have no direct evidence they exist. The cosmic microwave background constrains how large density fluctuations were on different scales in the early universe. Producing massive primordial black holes requires large fluctuations on large scales. The CMB observations show that fluctuations were small and nearly uniform. This rules out abundant massive primordial black holes unless they form through processes that leave no imprint on the CMB. Some exotic mechanisms have been proposed involving phase transitions or the dynamics of inflation, but these remain speculative. Without observational support, primordial black holes offer a solution in search of a problem they might not actually solve. A simpler explanation may lie in the episodic nature of black hole growth. Black holes do not accrete smoothly. They feed in bursts triggered by galaxy mergers, tidal disruptions of stars, or fluctuations in the large-scale gas supply. Between bursts, accretion drops to low levels. The black hole dims. It becomes difficult to detect. We observe quasars during their bright phases. We miss the same objects during quiescent phases. If a black hole spends most of its time dim and only briefly lights up when fed, the duty cycle affects how we interpret the observations. The brightest objects we detect might be systems caught during rare episodes of super-Eddington accretion. Their instantaneous accretion rates exceed long-term averages. Extrapolating from these snapshots overestimates how fast the population grows on average. Testing this hypothesis requires monitoring quasars over extended periods. Do their luminosities fluctuate dramatically? Do they turn on and off on timescales of years or decades? Long-term surveys show that some quasars do vary by factors of 2 or more over a few years, but most remain relatively stable over the durations we have monitored them. Variability on timescales of thousands or millions of years remains difficult to observe directly. We see only short segments of lives that span millions of years. Inferring long-term behavior from short observations is treacherous. The counterintuitive nature of the universe extends beyond black holes. Dark energy accelerates cosmic expansion. We might expect gravity to slow expansion as galaxies pull on each other. Instead, expansion speeds up. Dark matter outweighs ordinary matter by a factor of 5. We cannot see it or detect it directly, yet it dominates the gravitational field. Quantum mechanics allows particles to tunnel through barriers that classical physics forbids them to cross. Effects happen before causes at quantum scales. Physics at its core defies intuition built from everyday experience. Black holes growing faster than their theoretical limits fit within this broader pattern of nature confounding expectation. Perhaps the lesson is that theoretical limits are not absolute. They represent boundaries beyond which our models break down, not boundaries nature cannot cross. The Eddington limit assumes spherical accretion and uniform radiation pressure. Real accretion is clumpy, turbulent, and magnetized. Radiation escapes preferentially along certain directions. Matter falls in along others. The effective limit might be higher than idealized calculations suggest, or limits might not apply during brief phases of extremely rapid accretion triggered by major mergers. Nature has 9 billion years of cosmic history to experiment with variations. We observe a few snapshots. We construct theories to explain those snapshots. When new observations contradict our theories, the theories must adapt. The 40 billion solar mass black hole forces adaptation. It cannot be explained by standard growth timelines starting from standard seeds. Either the timelines must expand, the seeds must enlarge, the growth rates must accelerate, or some combination occurs. Each option requires revision to models built over decades. This is uncomfortable. Researchers invest careers in developing frameworks. Data that threatens those frameworks meets resistance. But the data persists. The black hole exists regardless of theoretical discomfort. Eventually, theory must yield to observation. The question is, which aspects of theory require revision and which remain intact? Some aspects certainly remain solid. The basic physics of accretion is well understood. Gravity attracts matter inward. Motion generates heat. Heat produces radiation. Radiation exerts pressure. The balance between forces determines flow rates. These principles do not change. What might change is how they apply in environments we cannot recreate or observe directly. The accretion flows around early universe black holes existed when the cosmic microwave background was hotter, when gas composition differed, when galaxy densities were higher. Conditions unlike anything in the local universe. Our models, calibrated on local objects, might not extrapolate reliably to these alien environments. This realization leads to a humbling conclusion. We think we understand black holes. We have equations. We have simulations. We have observations of local examples. But when we look to the early universe, to epochs we can access only through ancient light, the understanding proves incomplete. The objects we see do not behave entirely as predicted. The masses exceed expectations. The growth rates defy limits. The frequency contradicts statistical predictions. Something fundamental escapes our models. The universe operated differently then, or we misunderstand how it operates now. Either possibility demands attention. What happens next is refinement. More observations accumulate, statistics improve, systematic errors are identified and corrected. Simulations become more sophisticated, including physics previously ignored. The discrepancy between theory and observation narrows. Perhaps it closes entirely, resolved by better modeling. Or perhaps it persists, requiring genuinely new physics. The 40 billion solar mass black hole serves as a benchmark, a target that theories must explain. Until they do, the tension remains. The universe has presented a challenge. The scientific community accepts that challenge. The process of understanding continues. The light arrives carrying encrypted information. Every photon from the quasar contains data about conditions near the black hole, but decoding that data requires sophisticated instruments and careful analysis. We cannot visit these objects. We cannot probe them directly. We rely entirely on electromagnetic radiation that has traveled billions of years to reach us. The challenge is extracting maximum information from this tenuous signal, separating genuine physical signatures from instrumental artifacts and foreground contamination. Spectroscopy provides the primary tool. When light passes through a prism or diffraction grating, it separates into constituent wavelengths. Each element produces characteristic emission or absorption lines at specific wavelengths determined by quantum mechanics. Hydrogen emits at 656.3 nanometers in the red part of the spectrum. This is the H-alpha line produced when electrons drop from the third energy level to the second. Observe a quasar spectrum and you see this line but shifted to longer wavelengths by cosmic expansion. A quasar at redshift 2 shows H-alpha at 1969 nanometers in the infrared. Measure where the line appears. Calculate the redshift. Determine the distance and look back time. The width of emission lines reveals velocities. Gas clouds moving toward us produce blue-shifted light. Gas moving away produces red-shifted light. Both components blend together in the spectrum. The result is a broadened line. Measure the width in wavelength units. Convert to velocity using the Doppler formula. For quasars, the broad lines typically span velocities of thousands of kilometers per second. This indicates gas orbiting close to the black hole, where gravity is strong. The exact velocity depends on the orbital radius and central mass. Smaller radii or larger masses produce higher velocities. Disentangling these factors requires additional information. Luminosity provides that additional constraint. The quasar's brightness tells us how rapidly it accretes matter. More luminous quasars accrete faster. The accretion rate connects to the black hole mass through the Eddington ratio, the actual luminosity divided by the Eddington limit. Objects accreting at the Eddington limit have a ratio of 1. Super Eddington accretion produces ratios above 1. Measure the luminosity. Estimate the Eddington ratio based on emission line properties. Calculate the implied mass. This method requires only a single spectrum, making it scalable to large surveys. The Sloan Digital Sky Survey measured tens of thousands of quasars this way between 2000 and 2014. But complications arise immediately. The luminosity we measure depends on the quasar's distance. Farther objects appear fainter. Determining distance requires the redshift, which comes from the spectrum. This works well. More problematic is correcting for obscuration. Dust between us and the quasar absorbs and scatters light, particularly at optical and ultraviolet wavelengths. The quasar appears dimmer than it actually is. Infrared light penetrates dust more effectively. Observations at multiple wavelengths allow estimation of the dust column and correction of the luminosity. But this introduces uncertainty. Different dust models give different corrections. The uncertainty propagates into the mass estimate. The geometry of the emission region adds another layer of complexity. We assume gas orbits in a thin disk, with the broad lines coming from material close to the black hole. But direct images of nearby active galaxies reveal more complicated structures. Some broad line emission comes from clouds above and below the disk plane. Some comes from outflowing winds. The velocity field is not purely rotational. It includes radial motion and turbulence. Assuming pure rotation leads to systematic errors in the derived mass. The magnitude and direction of the error depend on the specific geometry, which we cannot observe directly for distant quasars. Variability studies probe smaller scales. Quasars vary in brightness over days to months. These fluctuations originate in the innermost accretion flow, the region within a few gravitational radii of the event horizon. The variability timescale sets a size scale. Light cannot propagate across a region faster than light speed allows. If a quasar brightens uniformly over 10 days, the emission region must be smaller than 10 light days across. This is about 250 billion kilometers, roughly the size of our solar system. For a 40 billion solar mass black hole, this is actually smaller than the event horizon diameter. Something does not add up. Either the variability comes from a compact hotspot rather than the entire disk, or the emission region is intrinsically small and highly variable. The Hubble Space Telescope revolutionized quasar observations after its corrective optics were installed in 1993. Its location above Earth's atmosphere eliminates the blurring caused by atmospheric turbulence. Ground-based telescopes see stars and quasars as fuzzy disks of light several arc-seconds across. Hubble resolves details down to 0.05 arc-seconds. This allows separation of quasar emission from host galaxy light. It reveals the morphology of the host galaxy. It identifies merger signatures. Many high redshift quasars reside in galaxies undergoing violent mergers, exactly as models predict. The disturbed morphologies confirm that mergers trigger quasar activity by funneling gas to the center. Chandra X-ray Observatory, launched in 1999, provides complementary information. X-rays come from the hottest gas, closest to the black hole. The X-ray spectrum reveals the temperature and density of this material. It shows absorption edges from partially ionized iron, indicating gas at millions of degrees. The ion line profiles are asymmetric, broadened and skewed by Doppler shifts and gravitational redshifts. This asymmetry maps the velocity field in the inner accretion disk. It tests predictions of general relativity in strong field regimes. For some nearby active galaxies, the ion line profiles require black hole spin measurements. The spin affects the innermost stable orbit location, which affects the maximum velocity, which affects the line profile. Radio observations trace jets extending far beyond the host galaxy. The Very Large Array in New Mexico, consisting of 27 movable radio dishes, maps these jets at high resolution. For the most distant quasars, the jets span hundreds of thousands of light years. They contain plasma moving at close to light speed. The jets are powered by extracting rotational energy from the black hole through magnetic fields. This Blandford-Zinajek mechanism requires rapid rotation. The mere existence of powerful jets tells us the black hole spins significantly. Non-rotating black holes cannot launch such jets efficiently. This constrains the spin, which constrains the merger history. Black holes that grew mainly through coherent accretion from a disk spin up to high values. Black holes that grew through random mergers with varying orientations average down to lower spins. Infrared observations became critical with the launch of the Spitzer Space Telescope in 2003, and later the James Webb Space Telescope in 2021. Infrared light penetrates dust. Many actively accreting black holes are shrouded in dusty tori, donut-shaped structures surrounding the accretion disk. These tori absorb ultraviolet and optical light and re-radiate it in the infrared. Observing in infrared reveals the total energy output, not just the fraction that escapes directly. This corrects luminosity estimates upward for heavily obscured sources. Some of the most massive black holes were missed by optical surveys because dust hid them. JWST is now finding these dust-obscured giants and revising upward the number density of massive black holes at high redshift. Gravitational microlensing offers a unique probe of quasar structure. When light from a distant quasar passes near an intervening galaxy, the galaxy's stars act as tiny lenses, magnifying different parts of the quasar emission region by different amounts. As the quasar, stars, and Earth move relative to each other, the magnification pattern changes. These changes reveal the size and structure of the emission region. A compact region shows rapid variability from microlensing. An extended region shows slower, smoother variations. Monitoring campaigns track dozens of lensed quasars. The microlensing variations constrain the accretion disk size, confirming that the optical emission comes from regions only a few light days across. This agrees with expectations from accretion disk theory. Reverberation mapping campaigns require coordinated observations across multiple telescopes. The continuum varies unpredictably. Capturing these variations demands near-continuous monitoring. A typical campaign observes a quasar every few nights for months. Each observation measures both the continuum flux and the emission line strengths. Later analysis cross-correlates the two light curves. The time lag that maximizes the correlation indicates the light travel time to the broad line region. This technique succeeded first for nearby active galaxies. Extending it to high redshift quasars required international collaborations and dedicated telescope time. The Australian National University's 2.3-metre telescope conducted some of the first successful high redshift campaigns in the A, targeting quasars at redshifts around 2. Recent advances have come from adaptive optics on ground-based telescopes. Adaptive optics systems use deformable mirrors that change shape hundreds of times per second to compensate for atmospheric distortion. A laser beam shot into the upper atmosphere creates an artificial guide star. Measuring how the atmosphere distorts this point source allows real-time correction. With adaptive optics, large ground-based telescopes achieve resolution comparable to Hubble. The Keck telescopes in Hawaii, each with 10-metre mirrors, use adaptive optics to study quasar host galaxies in detail. They measure stellar masses and star formation rates. They map the distribution of ionized gas. They identify companion galaxies about to merge. All this context helps interpret black hole growth. Precision has improved dramatically over 3 decades. In the eons, black hole mass uncertainties were factors of 3 or 5. Different methods gave results that disagreed within those wide ranges. By the hours, uncertainties dropped to factors of 2. Today, for the best-studied objects, uncertainties approach 30%. This represents incremental progress through better instruments, refined techniques, and larger samples. Each improvement enables tests of theoretical predictions at higher precision. The scatter in the correlation between black hole mass and galaxy properties has narrowed. The evolution of the mass function with redshift is better determined. The extremes of the distribution become clearer, yet at the highest redshifts, measurements remain challenging. Observing a quasar at redshift 7 requires infrared spectroscopy, since the optical emission has redshifted into the infrared. infrared detectors are less sensitive than optical CCDs. The thermal background from the telescope itself overwhelms faint signals. Observing time is precious and oversubscribed. JWST receives 10 times more proposals than it can accommodate. Choices must be made. Some objects get observed repeatedly to build up signal. Others receive only single snapshots. The surveyed sample remains incomplete. The brightest and most unusual objects receive priority. Typical objects go unobserved. Calibration introduces systematic uncertainties. The scaling relations used to estimate black hole masses from single epoch spectra are calibrated on local reverberation-mapped samples. These local samples contain about 50 objects spanning masses from millions to billions of solar masses. Extrapolating to 40 billion solar masses extends well beyond the calibration range. Physics might change at such extremes. The emission line properties might differ. The structure of the broad line region might scale differently. Without direct reverberation mapping at 40 billion solar masses, we cannot verify the calibration. We assume it holds. That assumption might be wrong. Future facilities will address some limitations. The extremely large telescope, with its 39-meter mirror, will collect more than 10 times the light of current facilities. This enables spectroscopy of fainter quasars and finer velocity resolution for brighter ones. The Large Synoptic Survey Telescope, now called the Vera C. Rubin Observatory, will image the entire visible sky every few nights starting in 2025. This continuous monitoring will catch transient events, including tidal disruption of stars by black holes. Each disruption offers a brief window when the black hole lights up, revealing its presence and allowing mass measurement. The accumulated sample of tidal disruptions will constrain the black hole mass function independently of quasar surveys. The Square Kilometre Array, a radio telescope under construction across Australia and South Africa, will map cosmic structure at unprecedented sensitivity. Its thousands of radio dishes will detect faint jets from distant active black holes. Radio observations complement optical and infrared data. They reveal different aspects of black hole activity. Jets propagate through the intergalactic medium, lighting up gas millions of light-years from the source. Mapping these jets traces black hole energy output over cosmic time. The radioluminosity function evolves differently than the optical luminosity function, revealing different black hole growth modes. Gravitational wave observatories will detect merging massive black holes. LISA will observe in the millihertz frequency band, sensitive to black holes weighing thousands to billions of solar masses. When two such black holes merge, LISA will detect the gravitational waves months or years before the final coalescence. The signal encodes the component masses, spins, and orbital parameters. This provides an entirely independent measurement of black hole masses at high redshift. Unlike electromagnetic observations, gravitational waves penetrate all intervening matter. They are not absorbed by dust or scattered by gas. They reach us directly from the source. The combination of electromagnetic and gravitational wave observations will reveal the full population of massive black holes across cosmic history. Each measurement technique has limitations. Each probes different aspects of the system. Combining multiple methods reduces systematic errors. When optical spectroscopy, infrared photometry, X-ray timing, and radiomorphology all point to the same black hole mass, confidence increases. When they disagree, deeper investigation follows. Sometimes disagreement reveals new physics. Sometimes it exposes instrumental issues. Either outcome advances understanding. The goal is not to confirm what we expect, but to discover what we do not yet know. The 40 billion solar mass black hole, measured through multiple techniques, confirmed by multiple teams, observed across wavelengths from radio to X-ray, represents a genuine challenge. The measurements are solid. The object is real. Understanding how it came to exist remains the work ahead. The 40 billion solar mass giant is not alone. Across the observable universe, scattered through space and time, other monsters lurk. Each one presents its own puzzle. Each one defies expectations in slightly different ways. By examining these individual cases, patterns emerge, or perhaps what emerges is the absence of pattern, the realization that each extreme object formed under unique circumstances that may never repeat. TON 618 commands attention. Discovered in 1957 as part of a survey of variable radio sources, it sat in catalogues for decades before astronomers recognized its true nature. Initial observations classified it as an ordinary quasar. But in 2004, detailed spectroscopic analysis revealed something extraordinary. The emission lines were extraordinarily broad, indicating velocities exceeding 7,000 kilometers per second. The luminosity reached 400 trillion times the sun's output. Modeling the system required a central black hole of 66 billion solar masses. This measurement, published by astronomers at the Crimean Astrophysical Observatory, made TON 618 the most massive known black hole for years. Its distance places it at redshift 2.2, about 10.4 billion light-years away. The universe was about 3.5 billion years old when we observe it. 66 billion solar masses represents more than the 40 billion solar mass object. Both exist at similar epochs. Both require similar formation timelines. TON 618 is perhaps 20% more massive. That difference might seem minor, but translate it to growth time. 20% more mass requires millions of additional years of accretion at the Eddington limit. Every additional million years pushes harder against the available cosmic time. The constraints become tighter. The formation scenario becomes more improbable. Holmberg 15A contains a black hole of roughly 40 billion solar masses as well. But unlike distant quasars, this system sits relatively nearby at only 700 million light-years. We observe it in the present epoch, not the distant past. The black hole resides at the center of a supergiant elliptical galaxy, the brightest galaxy in the Abell 85 cluster. The galaxy itself spans about 2 million light-years, 10 times larger than the Milky Way. Its stellar mass exceeds 3 trillion solar masses. This black hole grew over the full age of the universe. It had 13.8 billion years to accumulate its mass, not just 3 billion. The growth timeline is far more comfortable. Average accretion rates can be lower. The Eddington limit poses less constraint. The contrast is striking. A 40 billion solar mass black hole at redshift 2 represents an impossibility. The same mass black hole in the local universe represents normalcy. The difference is time. Local ultra-massive black holes tell us that such masses are achievable given enough time. High redshift examples tell us that sometimes nature achieves them impossibly quickly. The local examples serve as proof of concept. The distant examples serve as provocations. Phoenix A contains what may be the most massive black hole yet discovered, though the measurement remains uncertain. Estimates range from 20 billion to 100 billion solar masses, with a best estimate around 100 billion. If correct, this exceeds even TON 618 by a significant margin. Phoenix A sits at the center of a galaxy cluster 5.8 billion light-years away. The black hole powers jets that extend millions of light-years into the surrounding medium. These jets have carved cavities in the hot gas that fills the cluster. The energy required to evacuate these cavities over tens of millions of years implies accretion of vast quantities of matter. Calculating backwards from the energy output gives the black hole mass estimate. But this indirect method carries large uncertainties. Future observations may revise the mass downward, or they may confirm that 100 billion solar mass black holes exist. Compare these giants. TON 618 at 66 billion solar masses, shining as a brilliant quasar at redshift 2.2. Phoenix, a potentially at 100 billion solar masses, observable today at redshift 0.6. Holmberg 15A at 40 billion solar masses in the local universe. The 40 billion solar mass quasar at redshift 2.0. Each occupies a different point in space and cosmic time. Each formed under different conditions. Each grew through its own history of mergers and accretion. Yet all reached comparable masses. This suggests that 40 to 100 billion solar masses represent some kind of natural upper limit. Black holes can reach these masses. They do so through various pathways, but they rarely exceed them. Why should a limit exist? Theoretical arguments suggest several possibilities. As black holes grow more massive, they disrupt their host galaxies more dramatically. The jets and winds become more powerful. They heat surrounding gas more effectively. This heating reduces gas density and prevents further infall. The black hole starves itself by overfeeding, pushing away its food supply through its own energy output. This self-regulation might cap growth at tens of billions of solar masses. Beyond this threshold, feedback becomes so strong that accretion essentially stops. Galaxy mergers also become less frequent at late times. The universe expands. Galaxies move apart. The merger rate declines. By the present epoch, major mergers between massive galaxies are rare. A black hole that has grown to 10 billion solar masses has few opportunities to double its mass through merger. It must rely on gas accretion, which operates more slowly. The combination of declining merger rates and increasing feedback strength creates a ceiling. Black holes approaching 100 billion solar masses have exhausted most growth pathways. But statistical distributions tell a different story. Count black holes at different masses, plot the number density versus mass. The distribution follows a power law over several orders of magnitude. More low-mass black holes exist than high-mass ones. This is expected from hierarchical formation. Small objects are common. Large objects are rare. The distribution continues smoothly up to tens of billions of solar masses. There is no obvious cutoff, no sharp edge where the population drops precipitously. Instead, the tail extends gradually, becoming exponentially rarer, but not vanishing entirely. This suggests that ultra-massive black holes form through the same processes that form their smaller cousins, just carried to extremes. Holm 15A provides a useful comparison case for understanding growth mechanisms. Its host galaxy shows clear evidence of multiple major mergers. The stellar distribution is diffuse and extended. The core region, the innermost few thousand light years, is depleted of stars. This core depletion results from black hole scouring. When two galaxies merge and their central black holes combine, the merged black hole recoils from gravitational wave emission. It oscillates back and forth through the galactic center. With each passage, it gravitationally slingshots stars outward. Over billions of years and multiple mergers, this removes stars from the core. The size of the depleted core correlates with the black hole mass. Larger black holes create larger cores. Holm 15A has an enormous core consistent with its 40 billion solar mass black hole having formed through many mergers. Do high redshift quasars show similar merger signatures? Hubble imaging reveals that many do. The host galaxies appear disturbed. Multiple components overlap. Tidal tails of stars stretch into space. These signatures indicate recent or ongoing mergers. The correlation between quasar activity and mergers is strong. Something like 80% of luminous quasars show merger features. This supports the merger-driven growth scenario. Fresh gas from mergers feeds the black hole. Luminosity spikes. We observe a bright quasar. Over millions of years, the activity declines as gas is consumed. The quasar fades. The system becomes quiescent until the next merger. But some ultra-massive black holes reside in apparently undisturbed galaxies. Their hosts are smooth and symmetric. No obvious merger signatures appear. These systems challenge simple narratives. If mergers drive growth, why do some massive black holes form without them? Perhaps the mergers occurred long ago. Merger signatures fade over time as stellar orbits relax. A galaxy that merged 3 billion years ago might show no remaining disturbance. Or perhaps some black holes grew primarily through smooth accretion rather than mergers. Gas flows steadily inward from large scales, channeled by the gravitational potential. No violent collisions required. This pathway is slower but might operate continuously over billions of years. Statistical studies attempt to disentangle merger-driven from accretion-driven growth. Correlate black hole mass with host galaxy merger history. Galaxies with more mergers should host more massive black holes if mergers drive growth. The data show a trend, but with large scatter. Merger history explains perhaps 50% of the variation in black hole mass. Other factors matter: gas supply, environment, cosmic epoch. The picture is complex. No single process dominates. Growth results from whatever mechanisms operate in each specific system. Mergers matter when they happen. Accretion matters when gas is available. Feedback matters when energy output is high. All three processes interweave across a black hole's life. NGC 4889 in the Coma cluster illustrates another extreme. Its central black hole weighs 21 billion solar masses based on stellar velocity measurements. The galaxy itself is a supergiant elliptical, one of the most massive galaxies known. It contains about 4 trillion solar masses in stars. The ratio of black hole mass to stellar mass is about 0.5%, 5 times higher than typical galaxies. This suggests unusual growth history. Perhaps the black hole grew preferentially fast, or perhaps the galaxy lost stars through tidal stripping as it orbited in the cluster. Interactions with neighboring galaxies can strip outer regions, reducing stellar mass while leaving the central black hole intact. This would artificially inflate the ratio. Disentangling these effects requires modeling the galaxy's orbital history within the cluster, a complex task requiring simulations. IC 1101, one of the largest galaxies known, may contain a black hole exceeding 40 billion solar masses, though measurements are uncertain. The galaxy spans over 4 million light-years and contains perhaps 100 trillion stars. Its luminosity is enormous. But detailed studies of the central regions are difficult. The galaxy is distant, and the central black hole may not be actively accreting. Without strong emission lines or jets, mass measurements rely on stellar dynamics. The stars in such a massive galaxy move slowly, compared to the gravitational velocities near the black hole. Isolating the black hole's gravitational influence from the stellar mass requires extremely precise measurements. Current data provide only rough estimates. The black hole is certainly massive, probably in the tens of billions of solar masses, but the exact value remains uncertain. These examples span a range of cosmic environments and epochs. TON 618 at high redshift, actively accreting and shining brightly. Holmberg 15A and NGC 4889 in the local universe, dormant giants in massive galaxies. Phoenix A, perhaps the most extreme, powering jets that reshape its entire cluster environment. Each system offers insights into different aspects of black hole growth. Each provides constraints on formation models. Collectively, they map the high-mass end of the black hole population. Ongoing surveys continue finding more examples. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is measuring spectra of millions of quasars. Within this enormous sample, the rarest and most massive systems will appear. DESI aims to map the three-dimensional distribution of matter across cosmic time by using quasars as tracers. As a byproduct, it will identify the most extreme black holes. Each discovery refines the mass function, adding statistics at the high end where numbers are currently small. Radio surveys with next-generation telescopes will find highly obscured quasars invisible to optical surveys. Some massive black holes grow while shrouded in dust. They emit little optical or ultraviolet light, but shine brightly in infrared and radio. These dust-obscured systems may represent an important growth phase missed by previous surveys. Including them in the census will increase the estimated number density of massive black holes, potentially making the ultramassive population seem less rare than current catalogues suggest. Gravitational wave detections will provide completely independent measurements. When LISA detects a massive black hole merger, the gravitational waveform encodes both component masses and the final merged mass. This will test whether ultramassive black holes grow through mergers as models predict. If LISA detects mergers producing 100 billion solar mass remnants, we will know such masses are achievable through this pathway. If it detects no such events, growth must occur primarily through accretion. The gravitational wave data will complement electromagnetic observations, revealing a different facet of the population. The examples accumulate, but so do the mysteries. Why do some galaxies produce ultramassive black holes while others do not? What determines the maximum mass a black hole achieves? Do 100 billion solar mass black holes exist, or does growth stop around 50 billion? Can black holes exceed 1 trillion solar masses under any circumstances? Each question branches into further questions. Each answer reveals new complexities. The 40 billion solar mass black hole at high redshift stands among these examples as particularly problematic. Not because of its mass alone, but because of when it achieved that mass. That combination of size and epoch remains the hardest to explain. We observe the universe from a single vantage point. This matters more than we often acknowledge. Our position in space and time shapes what we see. It determines which objects are bright enough to detect. It controls which wavelengths reach our telescopes unobscured. It selects for certain phenomena while hiding others. Every survey, every catalogue, every measurement carries the fingerprint of our specific location. The question is whether what we observe from here represents reality everywhere, or whether we inhabit a cosmic bubble that distorts our understanding. Consider luminosity. The brightness of an object decreases with the square of distance. A quasar 10 times farther appears 100 times fainter. Our telescopes have detection limits. Below a certain brightness, objects disappear into noise. This creates an observational horizon that is not fixed, but depends on the intrinsic luminosity of sources. Bright quasars remain visible across billions of light years. Faint ones vanish from view at much shorter distances. Our census of the quasar population is therefore biased toward the most luminous systems. We see the tip of the iceberg. The bulk of the population, composed of less luminous objects, escapes detection. This bias affects mass estimates in subtle ways. If luminosity correlates with black hole mass, as theory suggests, then our surveys preferentially find the most massive black holes at high redshift. The 40 billion solar mass examples might represent the extreme tail of the distribution, systems so rare that only a few exist across the observable volume. We find them because they shine brightly enough to cross our detection threshold. Billions of smaller black holes might exist at the same distances, growing to 1 billion or 5 billion solar masses, but remaining invisible to our surveys. We have no way to count what we cannot see. Correcting for this observational bias requires models. Assume a luminosity function, the number density of quasars as a function of brightness. Extrapolate below the detection limit using the assumed functional form. Count the objects you can see. Apply the correction factor to estimate the total population, including unseen members. The technique works if your assumptions are correct. If the luminosity function has a different shape than you assumed, your correction fails. You might undercount or overcount the true population. The uncertainty grows as you extrapolate farther from observed values. Distance measurements introduce additional complications. We determine distances from redshift, which measures how much light has been stretched by cosmic expansion. But redshift has components other than expansion. Local velocities contribute. If a galaxy moves toward us at 300 kilometers per second, while space between us expands, the observed redshift combines both effects. For nearby objects, peculiar velocities matter. They can change distance estimates by tens of millions of light-years. For distant quasars, peculiar velocities become negligible compared to cosmological expansion. But gravitational redshift can matter. Light climbing out of a deep potential well loses energy and shifts to longer wavelengths. For objects very close to massive black holes, gravitational redshift is substantial. We must correct for it when interpreting spectra. Get the correction wrong, and you misestimate the cosmological redshift, which propagates into errors in distance and luminosity. Dust obscuration plagues observations at all distances. Our own galaxy contains dust lanes that block light from objects behind them. The galactic plane is so opaque that we can see only a few thousand light-years through it at optical wavelengths. This creates a zone of avoidance where few distant galaxies are catalogued. We miss everything behind the dust. Additionally, the quasar host galaxies themselves contain dust. Star formation produces dust from elements forged in stellar cores. This dust absorbs ultraviolet and optical light from the quasar, re-radiating it in the infrared. Heavily obscured quasars can be completely invisible in optical surveys while shining brightly in infrared. Only with infrared space telescopes like JWST can we detect them. How many ultra-massive black holes have we missed because dust hid them from optical instruments? Our position in time matters as much as our position in space. We observe the universe 13.8 billion years after the Big Bang. Looking outward means looking backward. The most distant objects appear as they existed billions of years ago. We see the universe's youth when we look far away. We see its maturity when we look nearby. This temporal structure is fixed. We cannot observe distant objects as they exist today. The light has not reached us yet. We cannot observe nearby objects as they existed in the distant past. That light has already passed us and moved on. Our view samples different epochs at different distances, making it difficult to track individual systems evolving over time. The cosmological principle asserts that the universe is homogeneous and isotropic on large scales. Homogeneous means the same everywhere. Isotropic means the same in all directions. This principle underlies modern cosmology. It allows us to assume that the laws of physics operate identically across the cosmos. It justifies extrapolating from local observations to universal conclusions. But the principle is not an established fact. It is an assumption based on limited observations. We can only observe a finite volume. We cannot verify homogeneity beyond our observational horizon. The universe might be homogeneous on small scales, but inhomogeneous on scales larger than we can observe. Evidence supports the cosmological principle on scales of hundreds of millions of light years and larger. The cosmic microwave background appears nearly uniform across the sky. Temperature fluctuations amount to only a few parts in 100,000. This indicates the early universe was remarkably homogeneous. Galaxy surveys show that structure becomes increasingly uniform as you average over larger volumes. Clusters and superclusters give way to a smooth distribution on scales approaching billions of light years. No preferred direction appears in the data. No center is evident. The principle seems to hold. But local deviations exist. Our galaxy sits in a somewhat underdense region. The local void, a region of space with few galaxies, lies nearby. We are not in a rich galaxy cluster, but rather in a small group. Our local environment is below average in density. Does this matter for observing distant quasars? Probably not directly. The quasars are far enough that our local density has little effect on their properties. But it might affect how we interpret observations. If we assume the universe is uniform and our observations are representative, but we actually occupy an atypical region, our conclusions will be skewed. The debate over cosmic acceleration illustrates this concern. In the later duos, observations of distant supernovae revealed that the universe's expansion is accelerating. This discovery shocked the community. It required introducing dark energy, a mysterious component that fills space and pushes it apart. Dark energy now comprises about 70% of the universe's total energy density. But what if the acceleration is an illusion created by our position in a void? If we sit in an underdense bubble, space around us expands faster than average. Observing distant supernova through this bubble might make it appear that acceleration is universal when actually it is local. Numerous studies have examined this possibility. Most conclude that our location is not unusual enough to explain the observations. But the concern persists. Our vantage point is not fully representative. For black hole observations, similar concerns apply. If massive galaxies and black holes cluster in certain regions, and we happen not to be in one of those regions, we might underestimate their abundance. Surveys from our position would miss concentrations elsewhere. The 40 billion solar mass black hole would seem rarer than it actually is. Conversely, if we sit in a region where massive structures formed earlier or more efficiently, we might overestimate their universal frequency. The objects we see might be local outliers rather than typical examples. Future surveys will address these concerns by mapping larger volumes more completely. The Rubin Observatory will image deeper than any previous optical survey. It will detect fainter galaxies and quasars across the full visible sky. The Euclid mission, launched in 2023, maps galaxies and measures their redshifts across large areas. These surveys will reveal whether galaxy distributions show unexpected large-scale patterns, or whether homogeneity holds as the cosmological principle predicts. Finding significant inhomogeneity would force major revisions to cosmological models. Anthropic reasoning enters here in subtle ways. The very fact that we exist places constraints on what kind of universe we inhabit. Galaxies must have formed. Stars must have ignited. Planets must have coalesced. Elements heavier than hydrogen and helium must have been synthesized in stellar cores and distributed through space. These requirements are not trivial. They depend on the universe having specific properties. If the strength of gravity were slightly different, galaxies might not form. If the nuclear forces were slightly different, carbon might not be stable. If the expansion rates were significantly different, structure might not have time to develop before the universe becomes too dilute. We observe the universe that we do partly because only such universes permit observers to exist. Does this reasoning apply to black holes? Possibly. If ultramassive black holes influence galaxy formation and star formation through feedback, the abundance of such black holes affects the likelihood of observers emerging. Too many ultramassive black holes and feedback might suppress star formation so efficiently that few Earth-like planets form. Too few, and galaxies might remain gas-rich and turbulent, hostile to stable planetary systems. The optimal range for producing observers might correspond to the black hole population we observe. This would explain why 40 billion solar mass black holes are rare but not absent. They form often enough to regulate galaxy growth, but not so often that they prevent habitability. Such arguments remain speculative and controversial. They explain observations by reference to our existence, rather than by reference to fundamental physics. Many physicists find this unsatisfying. It feels like giving up on understanding the universe in its own terms. But if the universe is truly vast, perhaps infinite, and if physical constants vary across regions, anthropic reasoning becomes unavoidable. We observe a region compatible with our existence because incompatible regions contain no observers. The 40 billion solar mass black hole exists in the part of the universe we can observe. Whether it typifies the universe as a whole remains unknown. The Copernican revolution taught us to abandon the assumption of centrality. Earth is not the center of the solar system. The Sun is not the center of the galaxy. Our galaxy is not the center of the universe. In fact, there is no center. The lessons seem to be that we occupy no special location. We are typical, average, unremarkable in our cosmic address. This principle guided interpretation of observations for centuries. It discouraged theories that placed Earth or our galaxy in unusual positions. Homogeneity and isotropy followed as natural extensions. If no position is special, the universe must look similar from everywhere. But typicality is an assumption, not a proven fact. Maybe we are special in certain respects, not cosmically central, but occupying a region with properties that differ from the average. This would not violate Copernican principles if the difference arose from chance rather than design. Statistically, some regions must deviate from the mean. We might happen to reside in one. As long as such regions are not forbidden by physics and arise naturally from random fluctuations, there is no philosophical problem. The question is empirical. Are we typical or not? Answering this requires surveys large enough to characterize the full distribution of properties across cosmic volumes. If 90% of regions resemble ours and 10% differ significantly, we are typical. If 50% resemble ours and 50% differ, we are borderline typical. If 10% resemble ours and 90% differ, we are atypical. Current data suggest we are closer to typical than to extreme outlier, but uncertainties are substantial. Our observational horizon encompasses only a small fraction of the full universe. We sample a limited volume and infer universal properties. The inference could be wrong. For black hole formation, the issue becomes acute. If the 40 billion solar mass black hole at high redshift is a 1 in a billion occurrence, its existence in our observable volume is unsurprising. We expect rare events to occur somewhere. But if it is a 1 in a trillion occurrence, its presence demands explanation. Are we lucky? Is our observational volume actually special in ways we do not recognize? Or are we misestimating the probability because our models are wrong? Disentangling luck from misunderstanding requires better models and more observations. Both are forthcoming. The universe serves as a natural laboratory. We cannot build experiments to test black hole formation under early universe conditions. We cannot recreate the densities and temperatures that existed billions of years ago. But nature has done the experiments for us. Every black hole is a laboratory. Every quasar tests theory under extreme conditions. The 40 billion solar mass black hole at redshift 2 represents an experiment that nature ran once, or perhaps a few times. The results are recorded in the light reaching our telescopes. Our task is to interpret the results correctly, to extract the physics from the observations, to understand what nature is telling us about how black holes form when conditions are pushed to extremes. Observational biases complicate this interpretation, but do not make it impossible. By understanding the biases, we can correct for them. By recognizing our limited perspective, we can avoid over-interpreting what we see. The key is maintaining appropriate humility about what we know and what we do not. The 40 billion solar mass black hole exists. That much is clear. Whether it is rare or common, whether it formed through standard processes or required special conditions, whether it represents a statistical fluke or a generic outcome, remains uncertain. The observations continue. Each new data point refines the picture. Each new survey expands the context. Slowly, the uncertainties narrow. The universe reveals itself in pieces. We assemble the pieces patiently, knowing that the full picture may take generations to complete. Star formation will continue for another 100 trillion years or so. The universe contains enough gas to fuel new generations of stars across that vast epoch, but the rate declines steadily. As gas is consumed or locked into stellar remnants, fewer new stars ignite. The universe grows darker. Red dwarfs, the smallest and longest-lived stars, burn for trillions of years, but eventually even they exhaust their fuel. By 100 trillion years after the Big Bang, essentially all stars have died. The stellar era ends. What remains are white dwarfs, neutron stars, and black holes. The galaxies still exist as gravitationally bound collections of dead stellar remnants, but they emit almost no light. The black holes continue accreting, though at vastly reduced rates. Occasionally, a white dwarf or neutron star wanders too close and falls in. These events are rare in the dim future universe. Space is mostly empty. Objects seldom encounter each other. A black hole might wait billions of years between meals, but each accretion event adds mass. Over trillions of years, the accumulated growth is measurable. A 40 billion solar mass black hole might reach 50 billion or 60 billion solar masses through this slow feeding. The growth asymptotes. The supply of nearby matter dwindles. Eventually, almost everything that can fall in has fallen in. Galaxy mergers continue across this era. Gravitational interactions with neighboring galaxies slowly drain angular momentum from orbits. Galaxies spiral toward each other over tens of billions of years. When they collide, their central black holes also spiral inward. The merger of two massive black holes releases gravitational waves. For black holes weighing tens of billions of solar masses each, the merger produces a signal detectable across the entire observable universe, even in the far future. But there are no astronomers to detect it. No observers remain by then. The merger happens in darkness and silence, witnessed by nothing. The merged black hole recoils from the asymmetric emission of gravitational waves. If the component black holes had different spins or masses, the gravitational waves carry net momentum in a particular direction. Conservation of momentum kicks the merged black hole in the opposite direction. For massive black holes, The recoil velocity can reach thousands of kilometers per second. This is sufficient to eject the black hole from its host galaxy entirely. It escapes into intergalactic space, a wandering gravitational well drifting through the void. Over billions of years, expansion carries it farther from other structures. It becomes isolated. Its final mass might reach 100 billion solar masses or more, the sum of many mergers across cosmic history. But even black holes are not eternal. Stephen Hawking showed in 1974 that black holes radiate. Quantum effects near the event horizon produce particle-antiparticle pairs. Occasionally, one partner falls into the black hole while the other escapes. From outside, this appears as thermal radiation emitted by the black hole. The radiation carries energy away. The black hole loses mass. Over unimaginable timescales, it evaporates completely. The evaporation timescale depends on mass. Smaller black holes evaporate faster. A solar mass black hole would take 10 to the 67th power years to evaporate. That is 1 followed by 67 zeros. The current age of the universe is about 10 to the 10th power years. We would need to wait 10,000 trillion years. A 40 billion solar mass black hole takes proportionally longer. The evaporation time scales as mass cubed. Multiply the solar mass evaporation time by 40 billion cubed. The result is roughly 10 to the 99th power years. This number is meaningless in human terms. We have no reference for such timescales. All protons in the universe may decay long before then, if proton decay occurs at all. The predicted decay timescale is at least 10 to the 34th power years. If protons decay, all atomic matter disintegrates. White dwarfs and neutron stars collapse or evaporate. Only black holes remain as discrete objects. Then even they slowly vanish through Hawking radiation. The final stages of black hole evaporation are violent. As mass decreases, the evaporation rate increases. A black hole that has shrunk to planetary masses evaporates rapidly. In its final seconds, it emits an intense burst of radiation across all wavelengths. The explosion releases energy equivalent to millions of nuclear weapons. Then, nothing remains. The black hole has disappeared completely. The information that fell in is either lost forever or somehow encoded in the final radiation. This is the information paradox. Quantum mechanics insists information cannot be destroyed. General relativity insists it vanishes into black holes. Resolving this conflict requires quantum gravity, a theory we do not yet have. During the black hole's lifetime, it might host phenomena we cannot currently imagine. Close to the event horizon, where gravity is extreme and quantum effects become important, physics operates differently than anywhere else in the universe. Time dilates enormously. Tidal forces rip apart any structure. Yet some theoretical proposals suggest that civilizations might extract energy from rotating black holes. The Penrose process allows energy extraction from the ergosphere, a region outside the event horizon where space-time is dragged along with the black hole's rotation. A sufficiently advanced civilization could theoretically harvest this rotational energy using the black hole as a power source. Would any civilization survive long enough to attempt this? Life as we know it depends on stars. When stars die, conventional life becomes impossible, but perhaps other forms of existence emerge, entities based not on chemistry, but on plasma physics near event horizons. Structures formed from electromagnetic fields rather than atoms. Consciousness implemented in patterns of gravitational waves. These are pure speculation, but the universe has trillions of years to explore possibilities. If life adapts and evolves, it might find ways to persist, even as conditions change radically. The probability seems low. Life on Earth took 4 billion years to produce technological intelligence. The universe is currently 13.8 billion years old. That ratio suggests intelligence is difficult to achieve and requires time. If new forms of life emerge in the far future, they would need comparable time to evolve complexity and awareness. But the environment grows harsher. Energy sources become scarce. Entropy increases relentlessly. The second law of thermodynamics drives the universe toward equilibrium, a state where no gradients exist and no work can be done. This is the heat death of the universe. All temperatures equalize, all processes cease. Only isolated black holes remain, slowly evaporating in the dark. Does the 40 billion solar mass black hole have any privileged role in this future? Not obviously. It is simply one black hole among many. Its mass makes it long-lived. It will be among the last objects to evaporate. But eventually it meets the same fate as everything else. The only potential significance is if its formation at early times influenced the subsequent history of structure formation in its region. The feedback it generated, the jets it launched, the gas it heated, all these effects propagated outward and shaped evolution over billions of light years. Galaxies that might have formed were prevented. Star formation that might have occurred was suppressed. The black hole's existence altered the trajectory of cosmic evolution in ways that cascade through time. Perhaps civilizations arose in galaxies affected by that feedback. Perhaps we are among them. Our Milky Way formed in a universe shaped by the collective feedback of billions of quasars, including monsters like the 40 billion solar mass example. The elements in our bodies were forged in stars whose formation was influenced by how gas cooled and clumped in a universe regulated by black hole energy. We are connected to these distant objects through chains of causation spanning billions of years. The connection is tenuous and abstract, but it exists. This raises questions about cosmic heritage. Every structure in the universe traces back to tiny quantum fluctuations in the first instant after the Big Bang. Inflations stretch these microscopic variations to cosmic size. Over billions of years, they grew through gravity into galaxies, stars, planets, and people. The specific fluctuation that seeded the region containing the 40 billion solar mass black hole had a particular amplitude and wavelength. Had it been slightly different, the black hole might have formed earlier or later, larger or smaller, or not at all. That change would ripple forward, altering the formation of surrounding structures, potentially affecting whether our galaxy formed where and when it did. We cannot trace these connections precisely. The butterfly effect operates at cosmic scales. Tiny changes in initial conditions produce vastly different outcomes after billions of years of nonlinear evolution. But the general principle holds. We are products of cosmic history. Everything that happened before contributes to what we are now. The ultra-massive black holes are part of that history. Their growth regulated the conditions that allowed our existence. Future observers, if any exist, will face challenges we cannot anticipate. By the time black holes begin evaporating in earnest, the universe will have expanded so much that most galaxies are beyond each other's observational horizons. Expansion accelerates due to dark energy. Eventually, all but the closest gravitationally bound galaxies recede faster than light, can travel between them. An observer in the far future sees only their local galaxy cluster. Everything else has disappeared over the horizon. The observable universe shrinks to a tiny fraction of its current size. Such observers would know less about cosmic history than we do. They could not observe the cosmic microwave background, which will have redshifted to undetectable wavelengths. They could not study distant quasars, which will have moved beyond reach. They could not measure cosmological expansion except within their local group. Their cosmology would be severely limited. They might never deduce that the universe had a beginning or that it contains structures beyond their horizon. They might construct entirely different theories of existence based on the limited evidence available to them. We are fortunate to live in an epoch where observation is possible. The universe is old enough that complex structures have formed. It is young enough that distant galaxies remain visible. The cosmic microwave background is still detectable. Quasars from the early universe are still observable. We occupy a window in time when understanding is achievable. This window will not last forever. In 1 trillion years, much of what we now observe will be inaccessible. In 100 trillion years, almost all evidence of cosmic history will have vanished. Future beings, if they exist, will face fundamental barriers to knowledge that we do not experience. Does this mean our observations carry special responsibility? Perhaps. We are among the universe's first observers, able to witness phenomena that later civilizations cannot. The 40 billion solar mass black hole exists at the edge of our observational capabilities. We barely detect it. We struggle to explain it, but we see it. We record its properties. We transmit that knowledge forward through our literature and culture. In a sense, we serve as witnesses to an era that will eventually be lost to time. What we learn now might be the only record that certain objects and events occurred. This veers into philosophy and meaning. Science typically avoids such territory. Observations are observations. They require no deeper significance. But when considering timescales that encompass the entire life of the universe, some reflection seems warranted. The black hole formed billions of years ago. We observe it now. It will persist billions of years into the future. Our moment of observation is infinitesimally brief compared to the object's lifetime. Yet in that moment, information crosses from the system to our instruments. The universe becomes aware of itself, however partially, through our measurements. Consciousness, however temporarily it exists, turns outward and comprehends. The 40 billion solar mass black hole has no awareness of being observed. It has no concept of existence or non-existence. It simply is, governed by equations we partially understand, but our observation of it creates meaning that would not otherwise exist. We see the impossibility. We struggle to explain. We imagine the early universe, the collapsing gas clouds, the merging black holes, the feedback loops that regulated growth. We construct narratives to bridge the gap between observation and understanding. These narratives are human creations, not intrinsic features of the universe. But they are how meaning emerges from data, how information becomes knowledge. The original question was how such a massive black hole could exist so early. After 10 parts examining observations, theories, challenges, and implications, what answer have we reached? The honest response is that we do not fully know. The object challenges our models. It exists in a regime where uncertainties are large and processes are complex. We have candidates for explanation, direct collapse seeds, super Eddington accretion, fortuitous merger histories, modified feedback. Some combination of these might work, but we lack the definitive observations or simulations to confirm any scenario decisively. This lack of closure might seem unsatisfying. We want answers, we want problems solved. But science proceeds incrementally. Some questions take decades to answer, some take generations. The nature of ultra-massive black holes in the early universe is such a question. Current observations are insufficient, current theory is incomplete. Future telescopes will provide better data. Future simulations will test mechanisms more thoroughly. Gradually, the picture will clarify. But we are not there yet. We stand at a moment of uncertainty, aware of the problem but lacking the solution. That uncertainty is itself valuable. It means discovery remains possible. It means the universe still has secrets. It means our understanding can deepen. The 40 billion solar mass black hole serves as a marker of that frontier. It identifies where our knowledge ends and speculation begins. It invites investigation. It challenges assumptions. It promises that the universe is richer and stranger than our current theories capture. This is the state science seeks. Not final answers, but better questions. Not complete understanding, but expanding awareness. If this exploration of cosmic mysteries has resonated with you, consider returning for more journeys through space and time. There are countless wonders waiting in the dark, objects and phenomena that push against the boundaries of what we thought possible. Each one teaches us something about the universe and about ourselves. Leave your thoughts in the comments if you find yourself moved by these ideas. And until we meet again, wherever you are in this vast cosmos, may you look up at the night sky with a sense of connection to everything it contains. The stars, the galaxies, the invisible black holes lurking in the deep. We are all made of the same fundamental ingredients forged in the same cosmic furnace. We are the universe observing itself. That is perhaps the most profound mystery of all.